Hello there and welcome to Physics with William, where curiosity gets cozy, science takes its shoes off at the door, and the universe is allowed to be mysterious without being in a hurry. Tonight, we are drifting toward one of the quietest ideas in modern physics, a particle so shy that if it passed through your body, your chair, your house, the planet beneath you, and kept going into the dark, it would probably do so without leaving so much as a polite note. Its name is the weakly interacting massive particle, though physicists, who are very fond of making large mysteries sound like kitchen appliances, usually call it a WIMP. It is not a confirmed particle. Not yet. It is a possibility, a suspect, a long-standing candidate in the search for dark matter, and it sits at the strange meeting point between what we know, what we can measure, and what the universe seems to be quietly hiding from us. So tonight, as you settle in, let me ask you something simple. Where are you listening from, and what does the night feel like where you are? Maybe it is late, and the room has gone still around you. Maybe there is rain at the window, or traffic far away, or the low hum of a refrigerator doing its small loyal work in the next room. Maybe you're watching from a bright morning somewhere, with coffee nearby, and the day only beginning to gather itself. Wherever you are, you're surrounded by matter. Your hands, your blanket, your walls, the air moving in and out of your lungs, every visible thing around you is made from familiar particles that like to interact, gather, collide, shine, warm up, cool down, and make themselves known. But according to the best evidence we have, all of that familiar matter is only a small part of what is really there. Most of the matter in the universe does not shine. It does not form lamps, clouds, trees, books, oceans, cats, teacups, or sleepy science listeners. It pulls with gravity, but it does not speak with light. It shapes galaxies, but refuses to glow. It seems to be everywhere, and yet when we reach for it, it slips through almost everything. That is where the WIMP enters the story, not with a dramatic crash, but with a very suspicious silence. A weakly interacting massive particle is imagined as something with mass, meaning it would contribute to gravity and help build the invisible scaffolding of the cosmos. But it would interact only very rarely with ordinary matter. It would not bounce off atoms in the eager way familiar particles often do. It would not get trapped easily. It would not announce itself with sparks or flashes in the ordinary course of things. It would pass through the world with an almost ridiculous level of indifference. If ordinary matter is like a busy town square with particles constantly bumping shoulders and exchanging little messages, a WIMP would be more like someone walking through at midnight, wearing soft shoes, touching almost nothing, and leaving everyone unsure whether anyone had been there at all. If you find this kind of gentle wandering through deep physics soothing, or if you enjoy having the universe explained slowly enough that it can become part science lesson and part bedtime companion, then I would be very grateful if you liked the video and subscribed. It helps this quiet corner of curiosity reach other people who may also be looking for a calm place to rest their thoughts. And please, do feel welcome to share where you are listening from, because there is something rather lovely about people in different rooms, cities, countries, and time zones, all pausing for a while to think about the same invisible universe together. It is a small reminder that science is not only about telescopes and detectors, but also about attention. It begins with someone noticing that the world is stranger than it first appears. The story of the WIMP begins with a much larger puzzle. When astronomers look at galaxies, they can measure how fast stars move around the galactic centre. In a simple picture, you might expect stars far from the centre to move more slowly, rather like planets far from the Sun moving along more leisurely orbits. But galaxies did not behave quite as expected. Their outer stars moved too quickly, as if some extra invisible mass was holding them in place. Without that hidden pull, many galaxies should have looked less stable than they do. They should have flung some of their outer stars away like sparks from a spinning wheel. But they did not. Something was there. Something with gravity. Something spread through and around galaxies in vast halos. something not visible through ordinary light. This was not the only clue. Clusters of galaxies also behaved as though they contained more mass than their stars and gas could explain. Light from distant galaxies bends as it passes massive objects because gravity curves its path, and this bending revealed extra mass as well. The early universe left behind a faint afterglow, a kind of cooled-down relic of its hot young state, and careful measurements of that afterglow also pointed toward a cosmos where ordinary atoms are only a modest fraction of the total matter. Again and again, in different ways and on different scales, the universe seemed to be telling us the same thing. There is more matter here than meets the eye. Not a little more either. A great deal more. Enough that the visible world begins to feel like foam on the surface of a very deep sea. Now, a sensible person might ask why we do not simply call this hidden stuff invisible dust, or cold gas, or faint stars, or old planets floating in the dark. Scientists did ask those questions. They looked carefully at whether dark matter might be made from ordinary objects that simply do not shine very much. Some ordinary dark things certainly exist. There are dim stars, wandering planets, black holes, cold gas clouds, and all sorts of difficult-to-see cosmic furniture. But when all the evidence is put together, ordinary matter cannot account for the whole mystery. The early universe itself tells us there is a limit to how much ordinary atomic matter can exist, because the amount of hydrogen, helium, and other light elements formed soon after the beginning depends on how many ordinary particles were around. The numbers do not allow ordinary matter to carry the full weight of dark matter. Something else seems to be required, something not made from atoms in the usual way. That is a strange thought, but not an unreasonable one. The universe is already full of particles that do not behave like the matter of everyday life. Neutrinos, for example, are real particles that pass through enormous amounts of matter almost without noticing it. Trillions of them stream through your body every second from the sun and from other cosmic sources, and you do not feel a thing. They are not dark matter in the full sense needed to explain galaxies, at least not the ordinary neutrinos we know, because they are too light and too fast-moving to build the right kind of cosmic structure. But they show us something important. Nature already knows how to make particles that are almost ghost-like. The idea that there might be another kind of hidden particle, heavier and slower, is not absurd. It is a reasonable guess made by people following evidence through the dark. The WIMP became one of the most attractive guesses because it seemed to fit several needs at once. It would have mass, so it could supply gravity. It would be stable, or at least long-lived enough to still exist today, so it could remain spread throughout galaxies after billions of years. It would interact weakly with ordinary matter, which would explain why we do not see it shining, colliding, or gathering into familiar objects. And in the early universe, if such particles were created naturally in the hot dense conditions shortly after the beginning, they might have been left behind in about the right abundance to match the dark matter we infer today. That last point made physicists especially interested. It suggested that the WIMP was not just an invented solution patched onto a mystery, but a particle that might arise naturally from deeper theories about matter and forces. There is a phrase sometimes used in this context, often called the WIMP miracle. We will not treat it as magic because physics has enough trouble without adding stage smoke. But the idea is that a particle with roughly the right mass and interaction strength could naturally freeze out of the early universe in a quantity similar to the amount of dark matter we observe. In the very young cosmos, particles were constantly being created and destroyed in a hot, dense bath. As space expanded and cooled, some particles could no longer find each other often enough to annihilate away. Their numbers would become fixed, like guests left standing in a ballroom after the music suddenly stops. For a WIMP, the timing of this freeze-out could lead to a universe filled with just the kind of invisible mass astronomers seem to need. It is one of those moments in science where a theoretical possibility leans very close to an observational mystery and whispers, "Perhaps I belong here." Of course, a whisper is not a discovery. A beautiful idea is not the same as a detected particle. This is where the story becomes both exciting and slightly frustrating. If WIMPs exist, then even though they mostly ignore matter, they should very occasionally interact with it. Not often, not easily. But perhaps once in a while, a WIMP drifting through Earth might strike an atomic nucleus inside a detector, giving it the tiniest nudge. That tiny nudge could produce a faint flash of light, a small amount of heat, or a subtle electrical signal. The challenge is that ordinary particles, cosmic rays, radioactive traces, and other background events can produce signals too. So scientists build detectors deep underground, beneath mountains or inside old mines, using layers of shielding and extremely pure materials, trying to create a quiet enough place to hear the smallest possible knock from the dark. There is something almost charming about that effort. Humanity, noisy as we are, has built underground rooms designed to be silent enough for the universe to confess. Imagine a tank of liquid xenon, or another carefully chosen material held in darkness, surrounded by instruments, waiting day after day for a particle that may pass through a light year of lead without caring, yet might, by rare chance, tap one nucleus in just the right way. It is patient work. It is not the sort of science where someone looks through a telescope and sees a new moon by breakfast. It is more like listening for one quiet footstep in a city during a thunderstorm, and then asking whether that footstep was truly what you hoped it was, or just a pipe cooling in the wall. The WIMP is also searched for in other ways. Physicists look for signs that dark matter particles might annihilate or decay somewhere in space, producing ordinary particles, light or radiation that telescopes could detect. They also use particle colliders, where known particles are smashed together at high energies, to see whether invisible particles might be created and carry energy away. If something invisible leaves the scene, scientists cannot see it directly, but they may notice that the visible debris does not balance in the expected way. It is a bit like entering a kitchen after midnight, finding crumbs, an open cupboard, and one very innocent-looking dog, then trying to reconstruct what happened without having witnessed the snack theft itself. So far, despite decades of searching, no WIMP has stepped forward and introduced itself. This does not mean the idea is dead, but it has changed the mood of the search. Early hopes were strong that WIMPs might appear in certain expected ranges, and experiments have tested more and more of that territory. Each new detector has become more sensitive. Each non-detection has narrowed the possibilities. The WIMP, if it exists, may be lighter than expected, heavier than expected, more weakly interacting than expected, or hidden behind more complicated behaviour. Or it may not exist at all. Science has to allow that possibility too. A good suspect is still only a suspect until the evidence holds. That may sound disappointing, but it is also how physics becomes honest. Nature is not obligated to choose the particle that makes our theories neatest. The universe does not check whether an idea has become popular at conferences before deciding what it is made of. Dark matter could be WIMPs, it could be axions, it could involve sterile neutrinos, hidden sectors, primordial black holes, or something not yet imagined clearly. It could even be that our understanding of gravity needs revision on cosmic scales, though many lines of evidence make the particle explanation very persuasive. The point is not that physicists have run out of ideas. The point is that the universe has given us a real problem, and every careful failure teaches us where the answer is not hiding. Still, there is a reason the WIMP remains worth understanding. It is not only a dark matter candidate. It is a window into how physicists think. It teaches us how an invisible particle can be inferred from gravity, constrained by cosmology, hunted in laboratories, and tested against the quiet refusal of nature to answer too quickly. It shows the relationship between the very large and the very small. Galaxies turning across hundreds of thousands of light years may depend on particles smaller than atoms. The shape of cosmic structure may be tied to events from the earliest moments of the universe. The darkness between stars may not be empty, but filled with something that passes through us constantly, without becoming part of our ordinary experience. That last thought is worth resting with for a moment. If WIMPs exist, then they are probably moving through this room right now, through you, through the walls, through the floor, through the earth itself. Not like wind, because wind pushes and cools and rustles leaves. Not like light, because light warms and illuminates. More like an unseen rain that almost never wets anything. You would not notice it. Your body would not notice it. The atoms in your bones would mostly carry on as if nothing had happened. And yet this invisible population, spread across the galaxy, could outweigh all the stars and gas and dust we see. It could be the quiet majority of matter, the part that does not gather into shining things, the part that gives galaxies their hidden grip. There is a humbling lesson in that. We are built from the kind of matter that interacts readily. Ordinary matter makes chemistry possible. Chemistry makes cells possible. Cells make sleepy viewers, curious minds, and channels where people spend an evening thinking about particles that barely interact at all. We are made from the social matter of the universe, the matter that clumps, glows, burns, freezes, dissolves, folds, and remembers. But the universe may be mostly made from matter that does none of those familiar things. Matter that does not make planets, does not make oceans, does not make lamps, does not make music, and does not stop for conversation. It simply gravitates. It gathers loosely around galaxies. It shapes the architecture of the cosmos without taking part in the bright little drama of atoms. That contrast is part of what makes the WIMP such a compelling idea for a calm science journey. It is not loud. It does not explode across the sky. It is not a monster black hole tearing apart a star or a supernova announcing itself across half the universe. It is quiet, almost comically quiet. Its whole personality, if a particle may be forgiven for having one, is that it has mass but almost no interest in touching anything. It is the universe saying that influence does not always require visibility. Something can be unseen and still shape everything around it. Something can pass through ordinary matter as if ordinary matter were hardly there and still hold galaxies together by gravity. We should be careful, though, not to turn mystery into certainty too quickly. The WIMP is a candidate, not a confirmed resident of nature. It is a carefully motivated idea, not a particle sitting in a museum display. Scientists have not directly detected it, and that fact matters. Good science does not only celebrate elegant hypotheses, it tests them, presses them, doubts them, improves them, and sometimes lets them go. The ongoing search for WIMPs is therefore not just a hunt for one particle. It is a test of an entire way of connecting particle physics to the history of the cosmos. Every underground detector, every telescope survey, every collider analysis adds another line to the conversation. Not always a satisfying line, perhaps, but a meaningful one. And that brings us gently to the path ahead. To understand what a WIMP really is, we first need to understand why physicists think there is invisible matter at all. We need to look at galaxies that spin too quickly, clusters that weigh too much, and light that bends around mass we cannot see. We need to ask why ordinary matter, for all its richness and beauty, cannot carry the full burden. Only then does the WIMP begin to make sense, not as a random invention, but as one possible answer to a question the universe keeps asking in gravity. So settle a little deeper now. Let the room be as quiet as it wants to be, and we can begin with the invisible weight that seems to surround the bright parts of the cosmos, holding galaxies in their slow turning shapes while the stars keep shining inside a much larger dark. The first clue that something heavy was missing did not arrive as a single dramatic announcement. There was no glowing object in a telescope, no new planet creeping across a photographic plate, no particle track curling neatly through a detector and making everyone in the room spill their tea. The clue came from motion. It came from the way stars and galaxies moved when astronomers added up all the visible matter and realized that the sums did not work. The universe, it seemed, was behaving as though it carried far more weight than it was willing to show. Not weight in the everyday sense of a suitcase that makes you regret packing a second pair of shoes, but gravitational weight, the deep ability of matter to pull on other matter and shape the motion of stars, gas, light, and entire galaxies. The visible universe was moving as though it were embedded in something larger, something unseen, something that did not shine but still had a grip. A good place to begin is with a galaxy. Picture one slowly turning in space, not as a flat drawing in a textbook, but as an enormous system of stars, gas, dust, and invisible structure, all rotating together across distances so large that human words begin to feel a little underqualified. A galaxy like the Milky Way contains hundreds of billions of stars, each star moving in an orbit around the galactic centre. Near the centre, there is more visible matter, more stars packed close together, more brightness. Farther out, the stars become thinner, the light fades, and the edge of the visible disk softens into darkness. If you were judging only by what you could see, you might expect the outer stars to move more slowly than the inner ones, because most of the visible mass appears concentrated closer to the centre. It feels sensible. It feels tidy. Nature, however, is under no obligation to be tidy, just because it would make our notebooks easier to read. When astronomers measured the speeds of stars and gas far from galactic centres, they found something surprising. The outer regions were moving too fast, not a little too fast in a way that could be blamed on a tired graduate student or an inconvenient smudge on a photographic plate. They were moving in a way that suggested a large amount of additional mass was present, extending far beyond the bright visible disk. Without that extra gravitational pull, those outer stars and clouds of gas should not have remained so comfortably attached to the galaxy. They should have been less orderly, less stable, more eager to drift away. Instead, they moved as though they were held by an enormous invisible halo. The galaxy was not merely the shining spiral we see in photographs. It was more like a lantern inside a much larger dark room, with the unseen room contributing most of the structure. This problem became especially clear through the work of astronomers who studied galactic rotation in careful detail. Vera Rubin is one of the names most closely associated with this story. In the late 20th century, she and her collaborators measured how stars and gas moved in spiral galaxies, and their results helped make the dark matter problem impossible to ignore. The measurements showed that galaxy rotation curves were often flatter than expected. In ordinary language, the outer parts of galaxies were not slowing down the way visible matter alone suggested they should. It was as if the galaxy had hidden mass spread throughout it. Mass that did not appear in the light but did appear in the motion. The stars were acting like witnesses, pointing not at what telescopes could see, but at what gravity could feel. There is something quietly powerful about that kind of evidence. We're used to thinking of astronomy as the science of looking. Telescopes gather light, images appear, colours reveal temperature, spectra reveal chemistry, and the distant universe becomes visible through patient observation. But dark matter reminds us that astronomy is also the science of inference. Sometimes the most important object in the room is the one that never appears in the photograph. You know it is there because everything else behaves differently around it. A curtain moves though you cannot see the breeze. A floorboard creaks though the hallway looks empty. Stars orbit too quickly, and the invisible announces itself through the visible. Galaxies were only the beginning. Clusters of galaxies, which are great gatherings of many galaxies bound together by gravity, also showed signs of missing mass. In these clusters, galaxies move around one another at high speeds. Hot gas fills the space between them, glowing in X-rays because it is heated to extreme temperatures. When scientists added up the mass of the stars and gas they could observe, the total was not enough to explain the cluster behaviour. The galaxies were moving too fast to remain bound unless more mass was present. The hot gas was sitting in a gravitational well deeper than visible matter could provide. Once again, the universe seemed to be carrying an invisible load. This was not a small accounting error. It was not like forgetting to add a few coins at the bottom of a shopping bag. The missing mass was enormous. In many systems, most of the gravitational influence seemed to come from matter that could not be seen directly. That is why dark matter is not simply a name for something dim. It is not ordinary matter that happens to be a bit shy with a lamp. It is dark because it does not interact with light in the usual way. It does not absorb light strongly. It does not emit light. It does not reflect light in any ordinary sense, yet it has mass, or at least it behaves gravitationally as if mass is there. The phrase dark matter is therefore both useful and slightly misleading. It sounds like a substance someone has already put in a jar and labelled. In reality, it is a name for a set of gravitational clues pointing toward something not yet directly identified. One of the most elegant clues comes from gravitational lensing. Light, for all its speed and brightness, does not travel through the universe completely indifferent to gravity. When light passes near a massive object, its path can bend. A galaxy cluster with enough mass can act like a vast natural lens, distorting and magnifying the images of more distant galaxies behind it. Astronomers can study these distortions and use them to map where the mass is. This is a remarkable idea. We cannot see dark matter directly, but we can see how its gravity changes the path of light from other objects. It is like noticing the shape of clear glass, not because the glass shines, but because the view behind it is warped. Gravitational lensing has revealed that the mass in galaxy clusters often extends beyond and around the visible components. In some especially important cases, lensing has shown a separation between ordinary matter and gravitational mass. One famous example is often called the bullet cluster, where two galaxy clusters have collided. The hot ordinary gas, which makes up much of the visible ordinary matter in the clusters, slowed down and piled up because gas interacts with gas, but the galaxies themselves pass through more easily because the space between stars is so vast. The gravitational lensing map showed that most of the mass was not centered on the hot gas, but was instead located closer to where the galaxies had moved. This fits the idea that dark matter passed through the collision mostly without interacting, while ordinary gas collided and lagged behind. It was not a perfect final answer, because science rarely hands us perfect final answers, but it was a striking piece of evidence that dark matter behaves differently from ordinary matter. The universe was giving the same message in several dialects. Galaxy rotation said there was extra mass. Galaxy clusters said there was extra mass. Gravitational lensing said there was extra mass. The pattern of the early universe said something similar too. Long before galaxies formed, the cosmos was hot, dense, and filled with radiation and particles. As it expanded and cooled, it left behind a faint glow that still fills space today. This glow carries tiny variations, slight differences in temperature from one direction to another, and those variations contain a record of what the young universe was made of and how matter began to clump. By studying that ancient light, scientists can estimate how much ordinary matter and how much dark matter must have been present to produce the universe we see today. The answer agrees with the larger story. Ordinary atoms are not enough. Some additional non-ordinary matter seems to be required. This matters because the dark matter problem is not based on one strange observation that might someday turn out to have a boring explanation. It is based on a network of evidence. Different methods, different instruments, different scales, and different physical processes all point in the same general direction. That does not mean every detail is settled. It certainly does not mean we know what the dark matter particle is, or even whether it is one particle at all. But it does mean that the invisible weight of the universe is not a casual guess. It is a conclusion drawn from the way gravity behaves across the cosmos. At this point, it is tempting to imagine dark matter as a kind of shadowy fog filling galaxies. That image is not terrible, as long as we do not take it too literally. Dark matter is thought to form large halos around galaxies, spread out much farther than the bright stars. It's not expected to clump into planets, rocks, or dark little pebbles in the ordinary way, because it does not seem to lose energy by emitting light. Ordinary matter can cool down. Gas clouds radiate energy away, collapse, form stars, build disks, and eventually become all the complicated furniture of the visible universe. Dark matter, if it interacts mainly through gravity, cannot cool and collapse in the same efficient way. It remains more diffuse, forming large extended structures that guide the formation of galaxies without becoming part of their bright atomic machinery. This difference is crucial. Ordinary matter is sociable. It interacts through electromagnetism. It forms atoms. It bumps, sticks, heats, cools, shines, and reacts chemically. That social behavior is why it can make dust grains, planets, oceans, cells, and eventually someone lying in bed listening to a soft explanation of invisible particles. Dark matter, by contrast, appears to be far less sociable. It participates in gravity, but it seems mostly uninterested in the interactions that make ordinary matter so rich and complicated. It does not form glowing clouds. It does not make dark stars in the same way ordinary gas makes bright stars. It does not sit in your hand, because it will not be caught by the forces that make your hand a hand. If it passes through you, it is not being rude. It is simply following a different set of rules. The scale of the hidden weight is difficult to appreciate. We live inside the visible world, so it naturally feels dominant. The table feels solid. The floor supports you. The sun rises, the moon shines, stars fill the night sky, when city lights are kind enough to step aside. But in the cosmic inventory, ordinary matter is not the main form of matter. It is the minority that glows, cools, collapses, and becomes chemically interesting. Dark matter seems to outweigh it by a large margin. So the universe we experience directly is not the whole structure. It is the visible trim on a much larger gravitational building. There is a useful humility in that thought. Human beings did not first discover dark matter by touching it, seeing it, or collecting it. We discovered the need for it by noticing that our visible universe did not have enough gravity to explain itself. That is a deeply scientific kind of humility, because it begins with a mismatch between expectation and measurement. You predict how a galaxy should rotate based on visible matter. You observe how it actually rotates. The two disagree. Then you test, improve, compare, and ask what could make the difference. The answer may be invisible matter, or it may require some adjustment in how we understand gravity. Physicists and astronomers have explored both routes, but many pieces of evidence, especially when taken together, strongly favour some additional form of matter rather than only a change in gravity. The debate has not vanished, but the particle dark matter picture remains the leading explanation because it can account for many observations at once. Still, one should be fair to the mystery. Dark matter is not directly identified. A careful person should not speak as though we have already shaken hands with it. We know there is a gravitational problem. We have strong reasons to think some unseen form of matter is responsible. We have excellent models describing how it behaves on large scales. But the microscopic identity remains unknown. It could be one kind of particle. It could be several. It could be heavy or light, warm or cold in the technical sense of how fast it moved in the early universe. It could interact with itself in subtle ways. It could belong to a hidden sector of particles with its own quiet rules. Among these possibilities, the weakly interacting massive particle became famous because it fit naturally into certain theories and offered a clear experimental target. But before the WIMP can be understood, the gravitational need for dark matter must be felt. The WIMP is not the beginning of the mystery. It is one proposed answer to the invisible weight already pressing on the universe. Think again of the Milky Way. Our galaxy is not merely the luminous band of stars you might see on a dark night. It is embedded in a much larger halo of unseen mass. The Sun, the Earth, and all of us are moving through this halo as the solar system orbits the galactic centre. If dark matter is made of particles, then those particles are likely passing through this region all the time. They would not be arranged in a neat wind with a smell or a temperature you could feel. They would not ruffle your hair or tap on the window. Their presence would be gravitational on the grand scale, and almost absent on the personal scale. This is one of the oddest features of the dark matter idea. Something can be cosmically dominant and locally unnoticed. It can help hold a galaxy together while slipping through a human body without leaving a sensation. That kind of invisibility is not unique in physics. Neutrinos also pass through matter with ease, and for a long time they were extremely difficult to detect. Yet neutrinos are real, measured, and woven into modern particle physics. They remind us that common sense, which is trained on tables and stones and mugs of tea, is not a reliable guide to what particles can do. A particle does not need to behave like dust in sunlight to be real. It may pass through planets. It may ignore detectors almost every time. It may require enormous patience and carefully shielded instruments to reveal itself. The lesson from neutrinos does not prove dark matter is a WIMP, but it makes the idea less strange. Nature already has a taste for ghostly particles. The invisible weight of the universe also shaped the history of cosmic structure. In the early universe, tiny density variations grew under gravity. Dark matter, because it did not interact strongly with light and ordinary radiation, could begin forming gravitational wells that ordinary matter later fell into. This helped galaxies form. Without dark matter, the story of structure formation becomes much harder to match with what we observe. Ordinary matter alone was coupled to radiation in the early universe in a way that delayed its collapse. Dark matter provided an unseen framework, a kind of gravitational scaffolding, allowing galaxies and clusters to develop in the pattern we see across space today. This is not scaffolding made of beams and bolts, of course, but of mass and gravity. It does not hold up a galaxy like a shelf holds books. It shapes the landscape through which matter moves. Large surveys of the universe show galaxies arranged not randomly, but in a vast cosmic web. There are filaments, clusters, walls, and immense voids where comparatively little matter gathers. Computer simulations that include dark matter can reproduce this web in striking ways. They begin with small variations in the early universe and allow gravity to amplify them over cosmic time. Dark matter clumps first, ordinary matter follows, gas cools, stars form, galaxies gather. The result resembles the universe we observe. Again, dark matter is not a decorative idea added after the fact. It helps explain the architecture. But there is a quiet irony here. Dark matter may have helped ordinary matter become interesting, while remaining almost entirely uninteresting by ordinary standards. It may have guided the formation of galaxies without forming flowers, oceans, or breakfast. It may have made the visible universe possible without becoming visible itself. In a sense, it is like the stage crew of the cosmos, never standing in the spotlight, yet responsible for much of the structure that allows the performance to happen. The stars get the applause. Dark matter moves the scenery. The next question is obvious and important. If the universe contains so much of this stuff, why has it been so hard to find directly? The answer lies in the word interaction. To detect something, it generally has to interact with your detector. Light interacts with camera sensors. Charged particles leave tracks. Sound moves air and reaches your ear. A smell means molecules have entered your nose, which is a very personal kind of measurement. But if dark matter barely interacts with the ordinary matter, then it can be abundant and still nearly impossible to catch. A dark matter particle could pass through a laboratory, through the walls, through the detector, through the bedrock beneath it, and through the rest of the planet without touching a single atomic nucleus. The universe may be full of it, but fullness does not help much if almost none of it stops to talk. This is why the dark matter problem sits at the boundary between astronomy and particle physics. Astronomy tells us that something is there through gravity. Particle physics asks what that something could be. Cosmology tells us how much of it the universe seems to contain, and how it shaped early structure. Laboratory experiments ask whether one of these invisible particles might occasionally bump into ordinary matter in a measurable way. The WIMP became a bridge among all these fields. It was heavy enough to matter gravitationally, weak enough to remain unseen, and theoretically plausible enough to inspire generations of experiments. Before meeting the WIMP more closely, it is worth holding the larger image in mind. The universe is not simply bright stars scattered in empty darkness. It is a gravitational system where most of the matter may be dark. The bright parts are easier for us to love because they make pictures, warmth, chemistry, and life. But the unseen parts may be doing much of the heavy lifting. When you look at a galaxy image, beautiful spiral arms glowing blue and gold, you are seeing only the luminous fraction. Around it and through it may be a much larger halo, not shining, not cooling into stars, not announcing itself in colour, but guiding the motion of everything visible. The photograph is not false, it is just incomplete. That incompleteness is not a failure of science. It is what makes science necessary. Every generation inherits a world that looks obvious until someone measures it more carefully. The heavens once seemed to turn around Earth. The stars once seemed fixed and eternal. The Milky Way once seemed to be the whole universe. Matter once seemed to be only the familiar stuff of atoms. Again and again, measurement has widened the room. Dark matter is one of those widening moments. It tells us that the universe is larger in content than it is in appearance. It tells us that gravity can reveal what light conceals. It tells us that the ordinary material from which we are made is not the cosmic majority, but a special, luminous, reactive minority. So when physicists talk about a weakly interacting massive particle, they are not inventing a ghost because ghosts are fashionable. They are responding to a real gravitational absence. They are asking what kind of particle could fill the invisible halos, shape galaxies, influence clusters, leave marks in the early universe, and yet pass through ordinary matter almost unnoticed. That question does not yet have a confirmed answer, but the road to it begins with the same simple observation, repeated in many ways across the sky. Things move as if more matter is present than we can see. Light bends as if more matter is present than we can see. The early universe evolved as if more matter was present than ordinary atoms allow. Somewhere behind the bright familiar cosmos is a hidden mass, quiet and patient, and the next step is to ask why the matter we already know cannot simply be stretched, dimmed, or hidden enough to solve the problem by itself. Ordinary matter is wonderfully busy. It is the kind of matter that makes itself known almost constantly. It shines when it is hot enough, reflects light when it is sitting quietly on a table, absorbs light when it is dark cloth or dust, bumps into other matter, sticks to other matter, heats up, cools down, crackles, dissolves, burns, freezes, melts, rusts, and very occasionally becomes a biscuit. It is the matter of stars and stones, of lungs and leaves, of oceans, planets, eyelashes, old notebooks, and that one mug you keep using even though there are perfectly good clean ones in the cupboard. It is so familiar to us that it can feel almost rude to suggest it is not enough. After all, ordinary matter seems to do everything. It builds the visible universe. It gives us chemistry. It makes galaxies glow. It forms the ground beneath our feet and the calcium in our bones. Surely if the universe is missing mass, perhaps ordinary matter is simply hiding somewhere, dim and cold and difficult to see. That would be the comfortable answer. Unfortunately, the universe has never shown much interest in giving only comfortable answers. At first, this idea seems reasonable. Space is huge, and not everything in it shines brightly. There are cold gas clouds drifting between stars. There are faint red dwarfs, small and long-lived, glowing so weakly they can be hard to notice from far away. There are brown dwarfs, objects too small to become proper stars, sitting in the twilight territory between planets and suns. There are rogue planets wandering without a parent star, dark as unlit stones in interstellar space. There are black holes, which are famous for not sending postcards. There is dust, frozen debris, dead stars, neutron stars, old stellar remnants, perhaps all sorts of dim cosmic leftovers tucked into the corners. So when astronomers first faced the missing mass problem, it was natural to wonder whether the missing weight might simply be ordinary matter in a dark disguise. This possibility was taken seriously. Scientists do not leap straight to invisible new particles unless ordinary explanations have been given a fair chance to sit at the table. For a while, researchers considered whether galaxies might be surrounded by huge numbers of faint objects made of ordinary atoms. These hypothetical dark objects could include dim stars, cold planets, stellar remnants, and other compact bodies too faint to detect directly. If enough of them existed, perhaps they could supply the gravity needed to explain galactic rotation and cluster behavior. It was a tempting idea because it did not require inventing an entirely new kind of particle. It only required the universe to have misplaced an enormous amount of familiar material in very inconvenient lighting. But ordinary dark objects have a problem. They are not completely invisible in every way. Even if they do not shine brightly, they can still reveal themselves through gravity, through absorption, through heating, through the effects they have on light, and through the way they form. A population of dark stars or wandering planets, large enough to account for all dark matter, would leave traces. Some would pass in front of background stars and briefly magnify their light through gravitational lensing. Some would contribute to the chemical history of galaxies. Some would be linked to processes that produce radiation, heavy elements, or other detectable signatures. When astronomers looked for these signs, they found that ordinary compact objects could account for some hidden mass, but not nearly enough. The universe could not hide the whole dark matter budget in a cupboard full of faint stars and lonely planets. There is also a deeper limit, one that comes from the early universe itself. Ordinary matter is made from particles that participate in familiar atomic physics, especially protons and neutrons gathered into atomic nuclei, with electrons arranged around them later as the universe cooled. In the first few minutes after the hot early phase of the cosmos, the conditions were right for simple atomic nuclei to form. Hydrogen, helium, and a little bit of other light material emerged from that early furnace. The amounts produced depended sensitively on how much ordinary matter was present at the time. If there had been far more ordinary matter, the recipe would have come out differently. The universe would have made different proportions of light elements. We can compare those predicted proportions with what we observe, and the result tells us that ordinary matter cannot make up all the missing mass. That point is important enough to slow down with. Dark matter is not just missing from our telescopes today, it is missing from the early universe recipe for ordinary matter. The amount of ordinary matter allowed by the formation of light elements is too small to explain all the gravity we observe in galaxies and clusters. So even if ordinary matter were hidden in very dim forms, there simply cannot be enough of it to account for everything. The cosmos keeps its receipts, and the early chemical record says ordinary atoms do not have the budget for the job. Another powerful clue comes from the ancient light left over from the young universe. This faint glow fills space in every direction, and it carries tiny patterns that tell us about the contents of the cosmos, when it was still very hot and dense. Those patterns are not random decoration. They are shaped by the amounts of ordinary matter, dark matter, radiation, and other ingredients in the early universe. Ordinary matter interacted strongly with light at that time. It was tied into a hot, glowing fluid, pushed around by radiation pressure, unable to simply collapse under gravity in the same way dark matter could. Dark matter, if it did not interact much with light, would behave differently. It would provide gravitational wells before ordinary atoms were free to fall into them fully. When scientists study the pattern in that ancient glow, they find that the universe needs both ordinary matter and non-ordinary dark matter. One cannot simply replace the other without ruining the pattern. This is one of those moments where the universe becomes strangely precise. We are not just saying there is too little visible stuff in galaxies. We are saying that the early universe had a measurable structure, and that structure tells us the invisible matter cannot mostly be the same kind of matter that makes stars, gas, and people. Ordinary matter leaves a particular fingerprint because it interacts with light. Dark matter leaves a different fingerprint because it mostly does not. The two fingerprints are not interchangeable. It is rather like listening to an orchestra from behind a wall and being able to tell that there are both strings and drums. You may not see the instruments, but the sound carries enough information to know that one section cannot be doing the work of the other. Ordinary matter also has a tendency to cool, collapse, and shine. This tendency is what makes the visible universe so interesting. Gas clouds can radiate energy away, lose heat, and fall inward under gravity. As they collapse, they form stars. Stars burn nuclear fuel and produce light. Around stars, leftover material can gather into planets. Molecules form. Chemistry begins doing its elaborate little dance. Given enough time and the right conditions, chemistry becomes biology, and biology becomes someone asking why ordinary matter is not enough. This ability to cool is essential. Ordinary matter can settle into disks, concentrate into dense objects, and build the complicated structures we recognize. Dark matter, whatever it is, seems not to behave that way. It does not appear to cool efficiently by emitting light. It does not collapse into thin, bright disks the way ordinary gas does. It forms broad halos around galaxies, large diffuse structures that extend far beyond the visible stars. This difference is another clue. If dark matter were ordinary matter, much of it should have joined the visible processes more strongly. It should have fallen into denser structures, heated, radiated, formed more compact objects, or otherwise left familiar signs. Instead, the dark component behaves as though it is less interactive, less able to shed energy, less willing to join the bright world of atoms. Imagine trying to gather a crowd of people into a quiet room. If everyone can talk, hear, bump into one another, notice the doors and respond to instructions, the crowd can organize itself. They can form lines, sit in rows, move toward the middle, complain about the temperature, and generally behave like a crowd. Ordinary matter is like that. It interacts constantly, which allows it to organize, cool, and settle. Now imagine a second crowd made of people who can only feel gravity and otherwise pass through one another and through the walls almost without noticing. That crowd cannot easily form a neat line. It cannot lose energy through conversation or friction in the usual sense. It remains spread out, moving through the space in a looser, ghostlier way. This is not a perfect analogy, because particles do not file complaints or ask where the biscuits are, but it gives the right feeling. Interaction is what allows matter to become complex. Lack of interaction keeps dark matter diffuse. This matters for galaxies. The visible disk of a spiral galaxy is relatively thin because ordinary matter can cool and settle. Gas clouds collide, radiate energy, and gradually flatten into a rotating disk. Stars form within that disk. Dust traces the spiral arms. But the dark matter halo is not a thin disk. It surrounds the galaxy more broadly. Its shape is inferred from gravity, from rotation, from lensing, from simulations, and from the motion of satellite galaxies. It behaves like a large invisible envelope rather than a bright flattened plate. That is not what we would expect if most of it were ordinary gas or ordinary dim material behaving according to electromagnetic forces. Cold gas might sound like a possible hiding place. After all, gas can be hard to see if it is not hot enough to glow brightly. But ordinary gas is still made of atoms, and atoms interact with light. Hydrogen gas, the most abundant ordinary element, has specific ways of emitting and absorbing radiation. Astronomers are very good at finding hydrogen in different forms, including through radio observations. Cold molecular gas can be more difficult, but it too has traces. Dust mixed with gas can block and redden light. Gas clouds influence star formation. If enough ordinary gas existed to explain dark matter, the consequences would be visible in many ways. It would not remain perfectly hidden, while also politely holding galaxies together. Black holes are another tempting hiding place. They're dark, compact, and gravitationally powerful. Could the missing mass be in black holes scattered through galaxies? Some black holes certainly exist, from stellar mass black holes formed by collapsed stars to supermassive black holes in galactic centers. There may also be primordial black holes, hypothetical objects formed in the early universe rather than from stars. But known stellar remnants cannot account for all dark matter without conflicting with observations of stellar evolution, element production, lensing events, and cosmic history. Primordial black holes remain an interesting possibility in some mass ranges, but they are not ordinary matter in quite the same simple sense, and they face many observational constraints. They may perhaps contribute something depending on their masses and abundance, but they do not provide an easy replacement for particle dark matter across the whole problem. The ordinary matter idea also struggles with galaxy clusters, where hot gas is visible in X-rays. In many clusters, most of the ordinary matter is not in stars but in extremely hot gas between galaxies. This gas shines in X-rays so it can be mapped, yet the total gravitational mass inferred from galaxy motions, hot gas behavior and gravitational lensing is much larger than the ordinary matter present. The gas is not missing. We can see much of it. It is simply not enough. The cluster is like a soup pot whose steam you can see, whose ingredients you can weigh, and whose gravitational pull still tells you there is another invisible ingredient taking up most of the mass. At some point, blaming unseen ordinary vegetables becomes difficult. Perhaps the most dramatic examples are cluster collisions. When galaxy clusters pass through each other, different components behave differently. Galaxies mostly pass by one another because the distances between stars are huge. Hot gas clouds collide, slow down, and become separated from the galaxies. Gravitational lensing can show where most of the mass is. In some systems, most of the mass follows the collisionless galaxies rather than the colliding gas. That is exactly what one would expect if a large dark matter component passes through with little interaction, while ordinary gas is slowed by electromagnetic forces. If most of the unseen mass were ordinary gas, it should behave more like the gas we observe, not like a nearly collisionless component. These cosmic collisions are messy, enormous, and complicated, but they offer a valuable natural experiment. They show that the main gravitational mass does not always sit where the ordinary matter is. This does not mean ordinary matter is unimportant. Quite the opposite. Ordinary matter is the part of the universe that gives us nearly everything we directly experience. It is the part that produces light, builds planets, makes chemistry, records fossils, forms clouds, and allows someone to fall asleep while learning about particle physics. It is precious. But being precious is not the same as being dominant. On cosmic scales, ordinary matter is like the illuminated part of a theatre stage. It contains the actors, the costumes, the dialogue, the dramatic gestures, and the occasional dropped prop. Dark matter is more like the hidden architecture supporting the building and shaping the space, not part of the visible performance, but essential to how the whole place holds together. One way to understand why ordinary matter cannot do the job is to think about the different kinds of evidence as independent locks on the same door. Galaxy rotation is one lock, galaxy clusters are another, gravitational lensing is another, the early formation of light elements is another, the ancient cosmic glow is another, the growth of the cosmic web is another. An ordinary matter solution has to open all of them at once. It cannot merely explain why one galaxy spins quickly. It must also explain why early element abundances look the way they do, why the cosmic microwave background has its observed pattern, why cluster collisions separate mass from gas, why large-scale structure forms as observed, and why there are not enough faint ordinary objects detected through lensing or other surveys. That is a demanding set of requirements. Ordinary hidden matter can open a few small locks, but the main door remains shut. This is where non-ordinary matter becomes less of a wild idea and more of a practical necessity. If the missing mass cannot be made mostly of atoms, then perhaps it is made of particles outside the usual atomic family. particles that have mass and feel gravity but do not interact with light, particles that do not form atoms, do not radiate energy efficiently, do not collapse into disks, and do not announce themselves through ordinary chemistry. Such particles would be dark not because they are painted black, but because light has almost nothing to do with them. They could be all around galaxies, passing through ordinary matter, shaping motion through gravity while ignoring nearly everything else. This is the conceptual doorway through which the WIMP walks. Very quietly, of course. A weakly interacting massive particle would not be made of protons, neutrons, and electrons. It would be a different kind of particle, one with mass, one that could have been produced in the early universe, one stable enough to remain today, and one that interacts so rarely with ordinary matter that it would not have been obvious in telescopes or laboratories. It would not solve every question simply by being named, but it fits the broad need for matter that gravitates without shining. It also connects the dark matter problem to particle physics, suggesting that the missing mass of galaxies may be linked to undiscovered particles governed by forces we only partly understand. The word weakly in weakly interacting massive particle can be a little confusing. It does not just mean weak in the everyday sense of a tired handshake after carrying groceries up the stairs. It refers to the possibility that the particle might interact through the weak nuclear force, or at least with a strength comparable to processes associated with that quiet part of particle physics. The weak force is real, important, and responsible for certain forms of radioactive decay and processes inside stars, but it acts over extremely short distances and does not make matter visible in the ordinary way electromagnetism does. A particle that interacts only through gravity and the weak force would be very hard to detect. It could pass through large amounts of matter with only a tiny chance of collision. That makes it frustrating for experimenters, but very suitable for dark matter. Massive is the other important word. A WIMP would have enough mass that, if many such particles existed, they could provide the gravitational pull inferred around galaxies and clusters. It would not need to be massive like a bowling ball or even like a dust grain. In particle physics, massive simply means heavier than very light particles such as ordinary neutrinos, at least in the versions that became popular as dark matter candidates. A huge number of such particles spread through the galaxy could add up to an enormous invisible halo. Individually, they would be tiny. Collectively, they could shape the cosmos. This is a familiar theme in physics. A single molecule of air is negligible to your hand. A whole atmosphere is enough to move weather systems and make umbrellas necessary. Why not neutrinos then? They are known particles, they barely interact, and they are abundant. This was a natural thought. Neutrinos do contribute a little to the matter content of the universe, but the ordinary neutrinos we know are too light and move too quickly, especially in the early universe. They are often called hot dark matter in this context, not because they are warm like soup, but because they moved at high speeds. Fast-moving dark matter washes out small-scale structure. It has trouble forming the kind of clumpy cosmic web that leads to galaxies as we observe them. The dark matter needed for galaxy formation appears to be mostly cold, meaning slower moving in the early universe, allowing structure to grow from small scales upward. WIMPs, being heavier, could naturally behave as cold dark matter. They would move more slowly and allow gravitational clumping in the right way. This distinction between hot and cold dark matter is not about comfort. It is about cosmic architecture. If dark matter moves too quickly, it smooths out small structures before they can grow. If it moves more slowly, it can gather into smaller gravitational seeds that later merge into larger structures. Observations of galaxies, clusters, and the cosmic web strongly favour a mostly cold dark matter picture. A good dark matter candidate must therefore not only be invisible and abundant, but also have the right motion history. Ordinary matter fails because it interacts too much with light and has the wrong cosmic budget. Ordinary neutrinos fail because they're too light and fast to make the observed structure. A WIMP seemed attractive because it could be non-ordinary, massive enough, slow enough, and weakly interacting enough all at once. There is an almost detective-like progression here. We begin with the crime scene, galaxies moving too fast. The first suspects are ordinary hidden things: dim stars, cold gas, rogue planets, black holes. Some are present, but none can account for the whole case. The evidence from the early universe rules out too much ordinary matter. Cluster collisions show mass behaving unlike ordinary gas. Neutrinos enter the room looking ghostly and promising, but their speed and lightness make them poor architects for the cosmic structures we see. Then the WIMP appears, not proven, not yet caught, but fitting the witness descriptions unusually well. Massive enough to matter, weakly interacting enough to hide, slow enough to help structure form, stable enough to still be here. It is no wonder physicists became interested. At the same time, this is where caution should remain in the room, perhaps seated comfortably near the lamp. The fact that ordinary matter is not enough does not prove that WIMPs exist. It proves that the main dark matter component, if the standard interpretation is correct, must be something beyond ordinary atoms. WIMPs are one candidate among several. Other ideas have their own motivations and searches. Axions, for example, are much lighter hypothetical particles connected to a different problem in particle physics. Sterile neutrinos are another possibility. Hidden sector particles could interact through forces unknown to us. Primordial black holes remain discussed in limited contexts. Science has not selected a winner. It has only ruled out many comfortable losers. Still, ruling things out is progress. It may not feel glamorous, but it is one of the ways knowledge becomes stronger. When experiments show that faint compact objects cannot supply all the dark matter, that matters. When early universe chemistry limits ordinary atoms, that matters. When cosmic background patterns demand both ordinary and dark components, that matters. When cluster collisions separate gravitational mass from hot gas, that matters. Each result narrows the mystery. The darkness becomes less vague. It is not just anything unseen. It must be something with a particular set of behaviours. It must gravitate. It must not shine. It must not interact too strongly with ordinary matter. It must fit early universe evidence. It must allow galaxies and clusters to form as they did. The unknown begins to acquire a silhouette. That silhouette is what makes the WIMP so useful as a teaching idea. Even if nature ultimately chooses another candidate, the WIMP shows the logic of the dark matter problem clearly. It embodies the properties needed to explain why ordinary matter is not enough. It lets us ask how a particle can be abundant yet invisible, massive yet nearly untouchable, cosmologically important yet personally unnoticed. It connects the motions of galaxies to the smallest scales of particle physics. And it gives experimentalists something to hunt for, not just a vague darkness, but a possible interaction in the detector, a possible missing energy signal in a collider, a possible faint byproduct from dark matter particles meeting in space. Perhaps the strangest part of all is that ordinary matter, despite being a minority, remains our only direct home. We are not made of the dominant matter, if dark matter is indeed matter in the particle sense. We are made of the complicated, interactive stuff. The stuff that cools into stars, builds planets, and produces chemistry. The stuff that writes equations on chalkboards, though tonight we're politely leaving equations tucked away. The stuff that makes tea, forgets where it put its keys, and wonders what the universe is made of. Ordinary matter may not be enough to explain the gravity of galaxies, but it is enough to ask the question. That is a rather beautiful imbalance. The rare luminous matter became conscious and noticed the quiet majority. So the reason ordinary matter is not enough is not one reason, but a convergence. There is not enough of it allowed by early cosmic chemistry. Its imprint on ancient light is different from what dark matter requires. It interacts with radiation too strongly. It cools and collapses too efficiently. It would leave more visible traces if it were hiding in large amounts. It does not match the behaviour seen in colliding galaxy clusters. It cannot build the cosmic web in the required way by itself. The universe needs something else, something less sociable than atoms, something that has gravity without the usual glow. And once that need is clear, the weakly interacting massive particle becomes easier to appreciate. It is not a random ghost placed into the story for atmosphere. It is an attempt to describe the kind of invisible matter that the evidence seems to demand. From here, we can finally move closer to the WIMP itself. Not just dark matter in general, not merely hidden mass or gravitational bookkeeping, but the particular idea of a particle that is massive, stable, and almost indifferent to the matter we know. A particle that may have filled the early universe, slipped out of thermal balance, and remained as a vast unseen population around galaxies. A particle that could be passing through Earth at this very moment, ignoring stone, metal, water and bone with the calm confidence of something that has crossed the galaxy without needing permission. To understand why physicists gave this candidate so much attention, we need to meet it on its own terms, not as a shadowy word, but as a proposed resident of nature with a very peculiar personality. Now that ordinary matter has politely failed the interview, we can invite the WIMP into the room and take a proper look at this very peculiar candidate. Not with a spotlight, of course, because if the WIMP exists, a spotlight would be almost completely useless. It would not glow under it, warm beneath it, cast a shadow in the usual way, or turn around and say, "Yes, terribly sorry, I am the missing mass you have been looking for." A weakly interacting massive particle is not the sort of thing that makes an entrance. It is more the sort of thing that may already be passing through the room while everyone is still looking at the door. The name itself sounds almost too convenient, as if physicists had discovered the particle first and then named it after its personality. Weakly interacting massive particle. It tells you nearly the whole idea in 4 words. Massive means it has mass, so it can contribute to gravity. Weakly interacting means it does not often collide with ordinary matter, does not easily exchange energy with it, and does not participate in the lively electromagnetic conversations that make ordinary atoms so visible and touchable. Particle means it is imagined as a genuine constituent of nature, something individual, countable in principle, part of the inventory of the universe, even if our instruments have not yet managed to catch it doing anything obvious. And when those words are shortened to WIMP, the result is a little funny, because the name sounds timid. In a sense, that is exactly the point. It is a particle with cosmic influence and almost no social presence. To understand why that combination is so appealing, it helps to compare it with the matter we already know. Ordinary matter is not shy. Electrons repel other electrons. Protons attract electrons. Atoms form. Molecules connect. Light bounces off surfaces and enters your eyes. When you place your hand on a table, the atoms in your hand do not truly merge with the atoms in the table. They resist one another through electromagnetic forces, and that resistance is what gives you the feeling of solidity. You feel the table because ordinary matter is constantly interacting with ordinary matter. On the tiny scale, the world is a crowded conversation. Particles are exchanging signals, responding to fields, arranging themselves into structures. The familiar world is touchable because its particles are, in a very real sense, very good at noticing each other. A WIMP would be different. It would not carry ordinary electric charge. If it did, we would likely have seen its effects already, because charged particles are not good at hiding. A particle with electric charge would interact with light, with atoms, with magnetic fields, with detectors, and with the material world in countless ways. Dark matter cannot behave like that. It must be neutral in the electromagnetic sense, or at least hidden from ordinary light so well that it remains effectively invisible across cosmic history. So the WIMP is imagined as electrically neutral, not tugged into atoms, not shining, not scattering light, not forming dark versions of chemistry in any simple, ordinary way. It would be there by gravity, but absent from vision. This is one of the most important points. A WIMP would not be dark because it is coloured black. Black paint is black because ordinary matter absorbs visible light. A black shirt is still deeply involved with light. It absorbs some wavelengths, reflects very little, warms in the sun, and can be photographed easily. Dark matter is dark in a much more radical way. It does not seem to care about light enough to absorb it, reflect it, or emit it in the usual manner. It is not like a black cat in a dark hallway. It is more like something that the hallway, the darkness, and the cat all fail to notice as it passes through. Yet the WIMP would not be nothing. That is the strange balance. It would have mass. It would contribute to the gravitational field of a galaxy. If there were enough WIMPs gathered in a broad halo around the Milky Way, their combined gravity could help explain why stars in the outer galaxy move the way they do. A single WIMP would be unimaginably small by everyday standards, but so is a proton, and the ordinary world is built from huge numbers of such tiny things. The question is not whether one particle is impressive on its own. The question is what a vast population of them can do together. A snowflake is light. A mountain glacier is not. A WIMP is tiny. A galactic halo full of WIMPs could be the hidden weight that keeps the visible galaxy in its observed shape. Massive in particle physics does not mean massive like a brick. It means the particle has a rest mass, and in the WIMP idea, that mass is expected to be much larger than the mass of very light particles such as ordinary neutrinos. The exact mass is not known because the particle has not been discovered, and different theories allow different possibilities, but the rough idea is that WIMPs would be heavy enough to move relatively slowly in the early universe, compared with light-fast particles. This matters because dark matter needs to help build structure. If the particles move too quickly, they smear out small clumps before galaxies can form properly. If they are heavier and slower, they can settle into gravitational patterns more effectively. They do not settle in the ordinary cooling sense, because they cannot radiate energy like gas, but they can gather gravitationally into halos and provide the scaffolding into which ordinary matter later falls. This is why WIMPs became associated with what physicists call cold dark matter. Cold does not mean icy to the touch. Please do not imagine a WIMP wearing a tiny scarf. It means that, in the early universe, the dark matter particles were moving slowly enough for small cosmic structures to grow. A universe filled mostly with fast light dark matter would form structure in a different way, one that does not match the observed pattern of galaxies and clusters as well. A WIMP, being massive, could behave as a cold dark matter particle, at least in the broad sense needed for cosmic structure formation. It would be invisible in light, quiet in ordinary matter, and useful in gravity. That is a good combination when the problem you are trying to solve is invisible gravitational mass. But where would such a particle come from? Physicists did not simply invent the WIMP as a label for whatever dark matter happens to be. The idea grew partly from theories that tried to extend the known family of particles. The standard model of particle physics is a remarkable achievement. It describes known elementary particles and the forces that act among them with extraordinary success. It includes quarks, electrons, neutrinos, and other particles, along with force-carrying particles connected to electromagnetism, the weak force and the strong force. It has survived many experimental tests. It is one of the great intellectual machines humans have built, and yet it is not complete. It does not explain dark matter. It does not include gravity in the same framework. It leaves open deep questions about why particles have the masses they do, why neutrinos are so light, why matter dominated antimatter in the early universe, and other mysteries that keep theorists awake in a much less soothing way than this video intends. Because the standard model is incomplete, physicists have explored possible extensions. Some of those extensions naturally predict new particles. In certain versions, the lightest new particle could be stable and electrically neutral. If stable, it would not decay quickly into ordinary particles. If neutral, it would not interact with light. If massive, it could supply gravity. If weakly interacting, it could remain hidden while still occasionally offering a chance of detection. That is exactly the kind of particle dark matter seems to ask for. So the WIMP was attractive not only because it fit astronomical evidence, but because particle physics already had reasons to suspect new particles might exist in the right general range. One famous theoretical setting that encouraged WIMP thinking was supersymmetry. This idea proposed that known particles might have heavier partner particles. We do not need the technical machinery here, and we certainly do not need equations, but the basic point is simple enough. Supersymmetry was designed to solve certain problems in particle physics, and in many versions it produced a stable neutral particle that looked like an excellent dark matter candidate. This candidate was often called the neutralino. For many years it was one of the classic WIMP examples. It had the right mood, if you like. Heavy, neutral, stable, reluctant to interact. The neutralino has not been found, and many simple versions of supersymmetry have been constrained by experiments, but the historical importance remains. It helped make the WIMP feel not like an artificial patch, but like a natural visitor from a broader theory. There were also other possible WIMP-like candidates from other theories, and the exact identity was never fixed. WIMP is a category more than a personal name. Saying WIMP is a bit like saying bird. It tells you some general features, but not whether you're dealing with a sparrow, an owl, or a suspiciously confident goose. A WIMP is any particle that roughly fits the idea of being massive, stable on cosmic timescales, electrically neutral, and interacting with ordinary matter only rarely, perhaps through the weak nuclear force or through another interaction of similar feebleness. That flexibility made the concept useful. It allowed experiments to search broadly without committing to one specific theory too soon. The stability requirement is easy to overlook, but it is essential. Dark matter has been around for a long time. The galaxies we observe today formed over billions of years. If WIMPs are the dark matter, then they must not decay rapidly into ordinary particles or radiation. They must persist from the early universe until now, still filling galactic halos, still moving through space, still holding their quiet gravitational role. A particle that existed briefly in the early universe but vanished long ago cannot explain the dark matter surrounding the Milky Way today. So a WIMP must either be truly stable or so long-lived that for all cosmic practical purposes it is still here. That raises an interesting thought. If WIMPs are still here, then they are not only in distant galaxies, they would be in our galaxy, and if they are in our galaxy, the solar system is moving through them. Earth is moving through them. You are moving through them. This is not meant as a spooky thought, though it is allowed to be a little strange. If the WIMP idea is right, then dark matter particles pass through ordinary matter constantly. They pass through the atmosphere, through buildings, through oceans, through mountains, through detectors, through people, and through the entire Earth, with hardly any chance of stopping. To a WIMP, a planet is not exactly transparent, because the chance of interaction is not absolutely zero. But it is transparent enough that most WIMPs would pass through without noticing. Earth would be less like a wall and more like a faint mist. This is the part where everyday intuition gives up and asks for a chair. We are used to matter being solid. Walls stop us. Floors hold us. Rain gets our clothes wet. A spoon does not fall through a table unless something has gone badly wrong. But solidity is not a universal property of all particles. It is a result of particular interactions. Ordinary matter feels solid because electromagnetic forces between atoms are strong and long-ranged compared with the tiny spaces involved. A WIMP, lacking those ordinary electromagnetic interactions, would not experience the wall as a wall. It would not be repelled by the electrons in the plaster. It would not care about the chemical bonds in concrete. It would not slow down because of friction in air. Most of the time it would pass through because there is simply no interaction available to stop it. This does not mean it is magical. It means it is governed by physics that gives it a tiny probability of interacting with atomic nuclei. If a WIMP does interact, it might strike a nucleus and make it recoil slightly. That recoil is the basis of many direct detection experiments. Scientists build extremely sensitive detectors and wait for the rare event in which a dark matter particle bumps into ordinary matter. The expected signal is small, and the backgrounds are many. Radioactive impurities, cosmic rays, neutrons, and other ordinary events can mimic or obscure what researchers are looking for. So the detectors are placed deep underground, where layers of rock help block cosmic rays. They are built from very pure materials. They are shielded and cooled and monitored with extraordinary care. The goal is to make a quiet room for a particle that almost never knocks. There is something very human about this effort. We suspect that the universe is full of something almost untouchable, so we build instruments of almost absurd delicacy and weight. We bury them beneath mountains. We fill them with noble liquids or chilled crystals. We measure flashes of light so faint that the word faint begins to seem insufficient. We argue with background noise. We count events. We compare seasons because Earth moves through the galaxy in a way that might slightly change the rate of WIMP interactions over the year. We do all this because even a particle that ignores matter might make one tiny exception now and then, and in that exception could be the first direct sign of the dark matter. A WIMP would also be searched for indirectly. If WIMPs can annihilate with one another, meaning two of them meet and produce other particles, then places with high dark matter density might produce detectable signals. The centre of the galaxy, dwarf galaxies and other dark matter-rich regions become places of interest. Telescopes look for unusual radiation or particle signatures that might come from dark matter annihilation. The difficulty is that the universe is full of energetic astrophysical processes. Pulsars, supernova remnants, cosmic ray interactions, black holes and other sources can produce signals that are hard to interpret. A suspicious glow in space may be dark matter, or it may be a more ordinary astrophysical object wearing a very convincing disguise. The universe has excellent plausible deniability. Particle colliders offer another route. If high-energy collisions can create WIMPs, the particles would escape the detector unseen. Scientists would not detect the WIMP directly. Instead, they would look for missing energy and momentum in the collision products, signs that something invisible carried part of the energy away. This is a clever approach, but it too is difficult. Many processes can produce invisible particles such as neutrinos, and the details depend on the theory. A collider might create a WIMP if the particle is light enough and interacts in the right way, but failure to see it does not rule out all WIMPs. It may simply be too heavy, too weakly coupled, or not produced by the available collisions. Dark matter is not required to make itself convenient. This is one of the reasons the WIMP search has become both exciting and sobering. For a long time, many physicists hoped that WIMPs would appear within reach of new detectors or colliders. The idea had theoretical motivation, experimental accessibility, and cosmological elegance. But as experiments became more sensitive, they did not find the expected signal. Large areas of possible WIMP behaviour have been ruled out. Simple models have been squeezed tightly. Some once popular candidates now look less likely. The WIMP has not disappeared, but it has become more elusive. It may be hiding in regions of parameter space that are harder to reach, or it may not be the dark matter at all. That might sound like a defeat, but it is better understood as the universe being specific. A failed search is not empty. It tells us what dark matter is not. It tells theorists which models are too simple, too optimistic, or too visible. It forces better experiments and broader thinking. In science, silence can be information if you listen carefully enough. When a detector hears nothing, and you know how sensitive it was, that nothing becomes a boundary. It says, if WIMPs exist, they must interact less often than this, or have masses outside that tested range, or behave differently from this model. The absence of a signal is not as glamorous as a discovery, but it sharpens the outline of the unknown. The personality of the WIMP, then, is almost a contradiction. It is massive but nearly absent. It is cosmically important but locally silent. It may fill the galaxy, yet one could pass through the palm of your hand without making the slightest difference to the warmth of your skin. It is not antimatter. It is not ordinary dust. It is not a tiny black hole in the usual WIMP picture. It is not a neutrino, though it shares the ghostly habit of ignoring matter most of the time. It is a proposed new particle, a dark relic from the early universe, possibly left over from a time when the cosmos was hot enough to produce particles we no longer see in ordinary conditions. Relic is a useful word here. The WIMP, if real, would be ancient. Not ancient like a fossil which formed long after stars and planets existed, but ancient from the earliest moments of the universe. It would have emerged from the hot particle soup of the young cosmos, when particles were colliding, transforming, appearing and disappearing in rapid balance. As the universe expanded and cooled, WIMPs would have stopped interacting often enough to remain in balance with ordinary particles. Their abundance would freeze into place, not literally freezing like water into ice, but becoming fixed because the universe became too spread out for them to keep annihilating efficiently. The remaining WIMPs would drift on, through the long history of cosmic expansion, through the formation of galaxies, through the birth of stars, through the making of planets, through the entire story that eventually produced us. That early universe origin is part of the reason WIMPs felt so compelling. They were not merely designed to explain galaxy rotation today. Their expected abundance could naturally come out near the amount of dark matter inferred from cosmology, at least in broad, simple versions. This was the famous attraction of the WIMP idea. A particle with weak scale interactions and a suitable mass could be produced in the early universe and leave behind about the right density. It was as though two separate puzzles, one from the larger scales and one from particle theory, leaned toward the same answer. Not proof, but a very interesting coincidence. Physicists are careful with coincidences. Sometimes they are accidents, sometimes they are clues. Much of the WIMP search has been an attempt to find out which kind this one is. A WIMP would not make dark matter clumps behave exactly like ordinary objects. Because it does not shed energy by light, it would not collapse into small dense bodies easily. It would form broad halos, moving in orbits through the gravitational potential of galaxies. These halos are not rigid shells, they are distributions of particles, with higher density near galactic centers and lower density farther out, shaped by cosmic history and gravity. Ordinary matter falls into these halos, cools, makes disks and stars and becomes visible. In this picture, the bright galaxy is nested within the dark halo, like a small glowing city inside a vast unlit landscape. The city is what we photograph. The landscape is what gravity remembers. The WIMP is almost untouchable, but not completely. That small difference is what gives the idea its experimental power. If it interacted literally only through gravity, direct detection would be far more difficult, perhaps nearly hopeless with current methods. But if it also interacts through the weak force or some other rare process, then a detector has a chance. Not a generous chance, not a friendly chance. More like the chance of hearing one snowflake land in a quiet field while wearing very good headphones. But science has often advanced by building better headphones. The weak force itself is a subtle character, and it deserves its own calm attention. It is not weak because it is unimportant. It is weak because, at the scales of ordinary particle interactions, its effects are far less obvious than the electromagnetism or the strong force, and it acts only over extremely short distances, yet it plays a crucial role in radioactive decay, in the processes that power stars, and in the transformations of particles. A WIMP tied to the weak force would live in a strange middle ground, not completely cut off from the standard model, but not friendly enough to be easily seen. It would be like someone who attends a party, stands near the wall, speaks to almost no one, and somehow still owns most of the building. What makes the WIMP so useful as a concept is that it gives the darkness a testable personality. Dark matter could have been a vague label for missing gravity forever. The WIMP made it concrete enough to hunt. It suggested interaction rates, masses, detection strategies, early universe histories, and possible signals. Even when experiments do not find it, they are learning something real. The WIMP gives science a way to ask nature a clear question. Are you made of particles like this? And nature so far has answered with a long quiet pause. That pause may mean no. It may mean not there. It may mean ask more carefully. It may mean the particle is more subtle than the simplest picture. The only way to know is to keep improving the question. There is a gentle irony in naming it weak. On cosmic scales, dark matter is not weak at all. Its gravity helps shape galaxies and clusters. It influences the growth of structure across billions of years. It may outweigh the ordinary matter that makes stars and planets. But in the laboratory, in the hand, in the detector, in the wall, it is almost powerless to announce itself. This is the strange split between gravity and interaction. Gravity accumulates. Even a weak gravitational pull becomes enormous when enough matter is involved across cosmic distances. But particle interactions are local and specific. A single WIMP passing through a detector has only a tiny chance of colliding. So dark matter can be dominant in the architecture of the universe, while nearly absent in the moment-to-moment experience of matter. It is powerful in the aggregate and shy in the particular. That idea can make the world feel slightly less solid, though not in a frightening way. The room around you is still made of ordinary atoms. The chair still holds you. The blanket still has weight and warmth. Nothing about dark matter makes ordinary reality less real. It simply adds another layer. Through the familiar world may pass another population of particles, almost untouched and almost touching nothing, not part of chemistry, not part of light, not part of life, but part of the gravitational story that made galaxies possible. You do not feel them because feeling is an electromagnetic event. Your nerves respond to ordinary forces. A WIMP does not pull those levers. It moves through, quiet as a thought you almost had and then forgot. Meeting the WIMP, then, means meeting an idea shaped by absence. We infer what it must avoid. It must avoid light. It must avoid frequent collisions. It must avoid decaying away. It must avoid being too fast in the early universe. It must avoid forming ordinary atoms. But it must not avoid gravity. It must have enough mass to matter. It must be abundant enough to shape galaxies. It must have been produced or left behind in the early cosmos. The particle is defined as much by what it refuses to do as by what it does. That is unusual, but not unscientific. Many discoveries begin with constraints. You learn the shape of a hidden object by walking around it in the dark and noting where your hands do not pass. And now, with this strange particle sitting before us as a possibility, massive, shy, ancient, neutral, nearly untouchable, the next natural step is to understand the quiet force that gives it part of its name. Weak interaction is not just a vague description. It points toward one of the fundamental forces of nature, a force that operates deep inside matter, changing particles, guiding radioactive decay, and helping the sun shine in its patient way. To understand why a particle could interact weakly and still matter greatly, we need to move from the galactic halo down into the small, precise world where particles transform, where the weak force works without drama, and where nature proves that even its quietest handshake can change the history of the universe. The weak force is one of those parts of nature that does not behave the way its name makes it sound. Weak in everyday life suggests something tired, hesitant, or not very important, like a kettle that takes too long to boil, or a handshake from someone who has clearly decided not to commit emotionally to the greeting. But the weak force is not unimportant. It is not a background detail. It is one of the fundamental ways particles interact, and without it, the universe would be a very different place. Stars would not work in the same way. Certain forms of radioactivity would not happen. Particles would not transform with the same delicate freedom. The sun would not shine as it does, and your quiet evening would be missing a rather essential lamp in the sky. It is called weak because compared with some of the other forces inside matter, its effects are much harder to notice at ordinary distances and ordinary energies. Electromagnetism is loud by comparison. It is the reason atoms hold together, light interacts with matter, magnets cling to refrigerators, and your hand does not pass through the arm of your chair. The strong force is louder still inside atomic nuclei, binding quarks and holding protons and neutrons together with extraordinary intensity over tiny distances. Gravity is extremely weak between individual particles, but it has infinite patience and adds up across planets, stars, and galaxies. The weak force occupies a strange place among them. It acts only over extremely tiny distances, far smaller than an atom, and it does not build the familiar structures of chemistry. It does not hold your mug together. It does not make light bounce into your eyes. It works quietly inside the particle world, changing one kind of particle into another, like a careful editor adjusting the hidden grammar of matter. That ability to change particles is one of the weak force's most important traits. Many forces push or pull, but the weak force can transform. It allows certain particles to become different particles. This is why it is essential in some forms of radioactive decay. In one common kind of radioactive decay, a neutron can turn into a proton while releasing other particles. This may sound like a small bookkeeping adjustment, but it is a deep transformation. A neutron and a proton are close relatives, but they are not the same. Changing one into the other changes the identity of the atomic nucleus. It can turn one element into another. It can alter the stability of matter. It is the sort of tiny event that, repeated across nature, becomes part of the larger story of stars, elements, and cosmic change. The weak force is also involved in the processes that let the sun shine steadily over billions of years. Deep inside the sun, hydrogen nuclei are squeezed together by enormous pressure and heat. But turning hydrogen into helium is not as simple as shoving pieces together like blocks on a table. Some of the particles must change identity along the way, and the weak force makes that possible. Because the weak force acts so rarely, the sun burns its fuel slowly. That slowness is a gift. If the processes inside the sun happen too easily, the sun might blaze through its fuel far more quickly, giving Earth a very different history, and life much less time to unfold. In a gentle and indirect way, the weakness of the weak force helps make long, stable starlight possible. Nature's quiet handshake, as it turns out, is one reason mornings exist. This is a useful lesson when thinking about WIMPs. A weak interaction can be rare and still matter enormously. A process does not need to happen often to shape the universe. If the setting is large enough or the timescale long enough, the weak force may be subtle, but it is woven into the behavior of particles and stars. Likewise, a WIMP, if it exists, could interact so rarely with ordinary matter that we almost never catch it. Yet a whole galaxy full of WIMPs could still provide a major gravitational influence. The rare and the important are not opposites. Physics is full of things that are difficult to notice locally but powerful in the long story. The weak force is carried by particles that are very heavy by particle standards. This heaviness is part of why the force has such a short reach. Electromagnetism can reach across large distances because its carrier, the photon, has no mass. The weak force's carriers are not like that. They are heavy, and because of this the weak force acts only over incredibly short ranges. It is less like a voice carrying across a valley and more like a message passed only when two people are standing almost impossibly close. Inside the tiny world of particles, that closeness can happen. In ordinary life, it never shows up as a push you can feel directly. This short range helps explain why weakly interacting particles can pass through matter so easily. To interact through the weak force, particles must come extraordinarily close in just the right way. Most matter is, on the scale of particles, mostly empty space. That phrase can be misleading, because ordinary matter feels solid thanks to electromagnetic forces. but nuclei are tiny compared with the size of atoms. A particle that does not feel electromagnetism can pass through the electron clouds of atoms without being stopped. It has to come close enough to a nucleus or another particle for the weak interaction to matter. Most of the time, it misses. Not because it is aiming, of course, but because the chance of the right encounter is very small. Neutrinos are the familiar example. They are not WIMPs, but they are excellent ambassadors for the idea of weak interaction. Neutrinos stream out of the Sun in enormous numbers. They pass through Earth constantly. Trillions pass through your body every second, and you do not feel them because they interact mainly through the weak force and gravity. Almost every neutrino slips through ordinary matter without collision. To detect them, scientists need enormous tanks of water, ice, or other materials, along with patient instruments watching for rare events. A neutrino can cross a vast amount of matter and still not hit anything. It is not supernatural. It is just very weakly interacting. The neutrino gives us a bridge to understanding the WIMP, but it also shows why the WIMP is different. Ordinary neutrinos are real and known, but they are too light and too fast to explain most dark matter. WIMPs are imagined as heavier particles, able to behave as cold dark matter, moving slowly enough in the early universe to help structure form in the way observations suggest. Still, the neutrino teaches the main emotional lesson, if particles may be allowed to have emotional lessons. A particle can be everywhere and almost undetectable. It can pass through your body by the trillions and leave no sensation. It can require enormous detectors buried deep underground or embedded in Antarctic ice just to catch the occasional whisper of its presence. If neutrinos can do that, then a hypothetical, heavier, weakly interacting particle begins to feel less like fantasy and more like a possible cousin from a hidden branch of nature. The weak force also has a peculiar relationship with identity. In the world of particles, identity is not always fixed in the comfortable everyday way. A chair does not become a lamp when left alone in the corner, unless someone has been doing very questionable interior design. But particles can transform under the right conditions. Through weak interactions, quarks can change type. Neutrons can decay. Certain unstable particles can turn into lighter ones. This mutability is essential for the way matter behaves at a fundamental level. The weak force is less like a glue and more like a permission slip for transformation. It tells matter that, in certain circumstances, one form may become another. That transformational quality is important in the early universe. When the cosmos was extremely hot and dense, particles collided with tremendous energy. The distinction between different particle processes was not experienced as it is in the cold, calm universe we live in now. Particles could be created, destroyed, transformed, and held in balance through rapid interactions. If WIMPs existed, they may once have been part of this early hot bath. They could have been produced in collisions and destroyed when they met their own kind, or perhaps their antimatter counterpart, depending on the model. For a while, creation and destruction might have balanced, keeping their abundance tied to the temperature and density of the universe. Then the universe expanded. It cooled. Particles became more spread out. Encounters became less frequent. For a weakly interacting particle, this matters greatly. If interactions are rare even under good conditions, then as the universe expands, there comes a time when the particle can no longer find partners, often enough to stay in balance. Its number becomes effectively frozen. Not frozen by cold in the ordinary sense, but frozen because the processes that would change its abundance become too rare. What remains continues through cosmic history. This is the basic reason WIMPs became so appealing as dark matter candidates. The weakness of their interactions could naturally leave behind a relic population from the early universe. That relic idea is strangely elegant. The dark matter in our galaxy today, if it is made of WIMPs, would not be something recently produced by stars or black holes. It would be ancient debris from the earliest thermal history of the cosmos. Every WIMP passing silently through Earth would be older than the planet, older than the Sun, older than the Milky Way in its present form. It would be a particle from the universe before there were stars to shine or atoms to gather into worlds. That does not make it mystical. It makes it cosmological. It means the present darkness around galaxies could be a fossil of the first moments, though not a fossil you could put behind glass in a museum, unless the museum had a detector of almost unreasonable sensitivity and a very patient curator. The weak force is also important, because it gives scientists a possible way to search. A particle that interacts only by gravity would be extraordinarily difficult to detect directly. Gravity between individual particles is so tiny that laboratory detection would be nearly impossible with current methods. But if a dark matter particle also feels the weak force, then it might occasionally collide with an atomic nucleus. That collision could produce a tiny recoil. In certain detector materials, that recoil might create a flash of light, a small amount of heat, or a handful of freed electrons. The signal would be faint, but not necessarily impossible. Weak interaction is therefore both the reason the WIMP hides and the reason we may have a chance of finding it. It closes the door most of the way, then leaves it open by the width of a particle. This is why underground dark matter detectors are built with such care. They are not simply waiting in the dark for drama. They are designed around the rare possibility that a WIMP, moving through the galaxy and then through Earth, might finally interact weakly with a nucleus inside the detector. The detector must be shielded from ordinary noise. Cosmic rays from space can create signals. Radioactive atoms in the surrounding rock, in the detector materials, or even in dust can create signals. Neutrons can mimic the kind of recoil expected from dark matter. The experiment has to become quiet in every possible way. It has to know its own materials, its own background, its own temperature, its own tiny flashes. It is a kind of scientific listening where nearly everything heard must first be suspected of being the room itself creaking. The weak force's role in detection also explains why WIMPs could be missed for so long. If their interactions are weaker than expected, or if their masses lie outside the most accessible ranges, then even large sensitive detectors may see nothing. This is not like searching for a lost shoe under the bed, where absence after a quick look strongly suggests the shoe is elsewhere. It is more like searching for one particular grain of dust that only becomes visible during a lightning strike on a Thursday. The absence of a signal is meaningful, but it must be interpreted through the expected interaction rate, detector sensitivity, and possible particle properties. A quiet detector does not always say there are no WIMPs. It may say that if WIMPs exist, they are more elusive than this detector can reveal. The word weak can also hide another subtlety. In physics, the weak force is part of the standard model, connected deeply to electromagnetism at high energies. At ordinary low energies, they appear very different. Electromagnetism is long-ranged and familiar, while the weak force is short-ranged and rare. But in the hotter, higher energy conditions of the early universe, these forces were more closely related. This matters because WIMPs are often imagined as belonging to energy scales, where the weak force and possible new particles might be connected. The details are technical, but the broad idea is simple enough. The early universe was not just a hotter version of your kitchen. It was a place where the hidden relationships among forces and particles could become more obvious. Particles that are inaccessible now might have been produced naturally then. This is one reason dark matter research brings together the smallest and largest scales. The weak force acts in the tiny interior of particle interactions. Dark matter shapes galaxies and the cosmic web. Yet the two may be linked because the early universe compressed particle physics and cosmology into the same story. A particle created through weak-scale processes in the young cosmos could later become the invisible mass holding galaxies together. That is a remarkable connection. A tiny handshake between particles in the first moments could echo as gravitational architecture billions of years later, not because the weak force itself holds galaxies together, but because it may determine how many dark matter particles survive to let gravity do the large-scale work. It is helpful here to separate two ideas that can easily blur together. The weak force would not be what makes dark matter gravitationally important today. Gravity does that. The weak force would be what lets WIMPs interact rarely with ordinary matter and what may have helped set their abundance in the early universe. Once the WIMPs exist in sufficient numbers, their mass creates gravity like any mass does. A WIMP does not need to interact weakly with a star in order to contribute to the galaxy's gravitational field. It simply needs to have mass and be present. The weak interaction is about detection and cosmic origin. Gravity is about the galactic effect. That distinction keeps the picture clean. Dark matter is seen through gravity, but it may be found through rare non-gravitational interactions. We infer it because galaxies rotate, light bends, and cosmic structure forms. We search for it by hoping it sometimes touches ordinary matter through something like the weak force. The evidence and the detection method are not the same. One tells us the hidden mass is there. The other tries to reveal what it is made of. The weak force provides one possible bridge from inference to identification. There is also a kind of modest beauty in the weak force because it reminds us that nature is not built only from obvious powers. A storm is obvious, a magnet is obvious, fire is obvious. The weak force is not obvious. You do not feel it as a push in your hand. You cannot see it bending a compass needle. Yet it helps govern the life of stars, the decay of particles, and perhaps the hidden matter of the cosmos. It works so far beneath ordinary experience that for most of human history, no one could have suspected it. And yet here it is, part of the machinery that makes the universe what it is. The quiet parts of nature often turn out not to be minor, just difficult to hear. For the WIMP, the weak force is the perfect kind of almost disconnected from us, but not entirely, almost invisible, but perhaps not forever, almost untouchable, but maybe capable of nudging one nucleus in a quiet underground detector, almost absent from ordinary life, but possibly central to the matter budget of the universe. This almost is why WIMPs are scientifically attractive. A completely untouchable particle would be hard to test. A strongly interacting particle would already have shown itself. The WIMP sits between those extremes. It is hidden enough to be dark matter, but not so hidden that experiments are hopeless in principle. That delicate balance is also why the search has become so demanding. If the original simple expectations had been right, perhaps WIMPs might already have appeared in direct detection experiments or at colliders. The fact that they have not tells us that either WIMPs are more elusive than the simplest version suggested, or dark matter is something else. This is not embarrassing for science. It is science doing what science does. A good idea is invited to faith measurement. If it survives, it becomes stronger. If it fails, the search moves on. The weak force opened a plausible path, but nature decides whether that path is the one actually taken. Even without a confirmed WIMP, understanding the weak force helps us understand why the idea made sense. Dark matter must ignore light, but it cannot necessarily ignore everything. It must be stable, massive, and abundant, but perhaps it has a tiny connection to known physics. The weak force is a natural candidate for that connection, because it already produces particles that pass through matter almost unnoticed. It already governs rare transformations. It already shows that something can be physically real while remaining almost completely absent from ordinary perception. In that sense, the weak force prepared our imagination. It taught us that the universe contains quiet messengers. So when we say a WIMP weakly interacts, we are describing a particle that may belong to this hidden style of nature. It would not be stopped by your skin, your walls, or the earth. It would not shine in a telescope. It would not form atoms with ordinary electrons. It would not gather into glowing clouds. But on very rare occasions, it might come close enough to an atomic nucleus to exchange a tiny amount of energy. That rare event would be the handshake, not a firm human handshake with eye contact and social expectations, but a particle handshake, brief, improbable, and almost silent. Nature does not need to be loud to be real. The next step is to return to the earliest universe, where this quiet handshake may have mattered most. Today, weak interactions are rare and difficult to detect, but in the hot, dense beginning, particles were crowded together in conditions far beyond anything in everyday life. WIMPs, if they existed, may have been created and destroyed constantly, until expansion stretched the universe thin enough for them to fall out of balance. Their abundance may have been set not by a cosmic decision, but by the simple fact that the universe cooled, spread out, and left some particles behind. This process, often called freeze-out, is one of the reasons the WIMP idea became so famous. It suggests that the dark matter around galaxies today could be the leftover population from a time when the universe was young, hot, and crowded, and when even the shyest particles still had enough chances to meet. To imagine the freeze out of a WIMP, we have to leave behind the calm, spacious universe we know and move our thoughts backward into a much younger cosmos. Not a universe with galaxies, not a universe with stars, not even a universe with atoms drifting about in the dark, but a universe so hot and crowded that matter had not yet settled into the familiar forms that make up rocks, air, water, and sleepy listeners. Everything was pressed into a dense, energetic state, where particles met one another constantly. They collided, changed, appeared, vanished, and reappeared again in a kind of restless particle weather. It was not chaos in the sense of being lawless. Physics was still physics. But it was a place where the rules played out with extraordinary speed and where particles that are rare or inaccessible today may have been made naturally, simply because the early universe had enough energy to make them. This is where the WIMP becomes more than just a possible particle hiding in the galaxy today. It becomes a relic. If WIMPs exist, they may be leftovers from that early hot period, survivors from a time when the universe was young enough and energetic enough to produce them in great abundance. That idea is one of the reasons physicists took WIMPs so seriously for so long. They were not merely invented to fill a gap around galaxies. They could have a natural origin in the thermal history of the cosmos. The same expanding universe that cooled enough to let atoms form, stars ignite, and galaxies gather may also have cooled in such a way that a population of weakly interacting massive particles was left behind, spread through space, invisible to light, waiting for gravity to gather them into the great dark halos we infer today. In the earliest moments relevant to this story, the universe was like an incredibly hot particle bath. Ordinary particles and possible dark particles were not sitting separately in neat categories. They were part of a crowded environment where energy could turn into particles, and particles could turn back into energy or into other particles, as long as the rules of nature allowed it. A WIMP and its partner, depending on the theory, might meet and disappear into lighter particles. Lighter particles might collide with enough energy to produce WIMPs again. The important point is balance. When the universe was hot and dense, reactions happened often enough that the number of WIMPs could adjust to the conditions around them. If the temperature was high enough, making WIMPs was possible. If WIMPs were too abundant, they could annihilate away. The particle population was constantly negotiating with the universe, not consciously, of course, but through collisions and probabilities. This balance is called thermal equilibrium, though we can think of it more gently as a busy market where particles are constantly trading identities. In such a market, nothing stays fixed for long. If one kind of particle becomes less common, interactions can produce more of it. If it becomes too common, interactions reduce it. The whole system keeps adjusting because particles are close together and meeting often. A WIMP in this early phase would not yet be the almost untouchable drifter we imagine passing through Earth today. It would still interact weakly, yes, but the universe was so dense that even rare interactions had many opportunities to occur. If you are in a room with only 2 people, a shy person may speak all evening to no one. Put that same shy person in a room packed shoulder to shoulder with thousands of people, and leave them there long enough, and eventually even they may have to say, "Excuse me." The early universe was that crowded room. except hotter, smaller, and very much lacking refreshments. Then expansion changed everything. Space stretched, the universe cooled, particles became less energetic and more spread out. Interactions that had once been frequent became less common. For a massive particle like a WIMP, the cooling was especially important. As the universe lost temperature, producing heavy particles became harder. The lighter particles no longer had enough energy in their collisions to create WIMPs easily. Meanwhile, WIMPs that already existed could still meet one another and annihilate, reducing their number. So for a while, the WIMP population began to fall, creation slowed down, destruction continued, the balance shifted. But destruction also depended on encounters. A WIMP had to find another suitable particle to annihilate with, and as the universe expanded, finding partners became harder. The particles were farther apart. The cosmic crowd thinned. At some point, the universe expanded faster than WIMPs could find each other efficiently. The reactions that had kept their abundance in balance became too rare to continue. Their number stopped changing much. What remained was carried forward by the expanding universe. This is the freeze-out. Nothing froze like water turning to ice. No little dark matter snowflakes formed. The word describes a number becoming fixed because the universe became too thin and too cool for the old interactions to keep up. It is a simple idea with enormous consequences. The amount of WIMP dark matter today would be determined by when those particles fell out of equilibrium in the early universe. If WIMPs interacted more strongly, they would keep finding one another longer and annihilate more efficiently, leaving fewer behind. If they interacted more weakly, they would stop meeting earlier, leaving more behind. In this way, the abundance of dark matter becomes linked to the strength of its interactions. That is part of what made the WIMP idea so appealing. A weak interaction strength, in the broad range physicists were already interested in for other reasons, could naturally leave behind an amount of dark matter similar to what the universe appears to contain. It was not exact proof, but it was suggestive enough to make many people sit up a little straighter. This is sometimes described as a coincidence that looked too good to ignore. The particle needed for dark matter had to be massive, stable, and hard to see. Particle theories beyond the known standard model often suggested new, massive particles that could be stable. The early universe could produce such particles. If they interacted with roughly weak force strength, their freeze-out abundance could land near the observed dark matter density. Several pieces seemed to fit. Not perfectly, not uniquely, but neatly enough to inspire decades of searches. Physicists like neatness when it survives contact with measurement. It gives a sense that nature may be trying to tell a coherent story, even if she insists on mumbling the crucial parts. The freeze-out picture also explains why dark matter could be everywhere without being created by stars or galaxies. WIMPs would not need to be produced recently. They would not come from supernova, black holes, or decaying ordinary matter. They would already be there, spread through the universe from early times. As gravity amplified tiny variations in density, WIMPs would gather into clumps and halos. Ordinary matter would later fall into those gravitational wells, cool, form stars, and light up the visible galaxies. In that sense, the dark matter would be older than the shining structures it helped shape. The hidden framework came first, and the bright architecture followed. It is worth slowing down over that image because it changes how we think about the cosmic timeline. We often picture the universe becoming interesting when stars ignite. That is understandable, because stars are visible and dramatic. They give us light, heat, elements, planets, and eventually biology. But if the WIMP picture is right, then the invisible matter was already playing its part before the first star existed. It was not glowing, it was not making atoms, it was not forming chemistry, it was simply present, moving under gravity, gathering slowly into regions that would guide future structure. The first galaxies may have formed inside dark matter halos, as ordinary gas fell inward and began to shine. The darkness did not arrive after the light. The light may have gathered inside the darkness. The freeze-out process depends on the universe doing two things at once: cooling and expanding. Cooling changes what kinds of particles can be created easily. Expansion changes how often particles meet. Both matter. If the universe cooled but did not expand, particles might remain crowded enough to keep interacting. If it expanded but stayed extremely energetic, heavy particles might continue being produced. But the real universe did both. It stretched and cooled, and in doing so, it turned a once lively particle population into a relic. The WIMP, if real, is not simply hiding because it is shy. It is also stranded in a sense left over from an earlier era, when the conditions that made and destroyed it were common, but which no longer exist in the same way. This is not unique to WIMPs. The universe contains several relics from its early history. The faint background light that fills space is a relic from a time when the universe first became transparent to light. The light elements formed in the first few minutes are relics of early nuclear reactions. Neutrinos from the early universe should also remain as a cosmic background, though they are very difficult to detect directly. A WIMP relic would fit into this broader pattern. Cosmology is, in many ways, the art of reading leftovers. The universe cooled, changed, and moved on, but it left traces behind. Some traces glow, some are chemical, some are gravitational. WIMPs would be a gravitational relic, silent and persistent. The word annihilation can sound violent, but in particle physics it simply means particles meet and transform into other particles or energy allowed by the rules. In the early WIMP story, annihilation is essential because it reduces the number of WIMPs as the universe cools. Later, after freeze out, annihilation becomes rare because the particles are too spread out, but it may not stop completely. In dense regions such as galactic centers or smaller dark matter-rich systems, WIMPs might still occasionally encounter each other and annihilate. If that happens, the products might include ordinary particles or radiation that telescopes could detect. This possibility motivates indirect searches for dark matter. Scientists look for unusual signals from regions where dark matter density should be high. The challenge, as always, is that the universe contains many ordinary sources of energetic radiation. A possible dark matter signal has to be separated from astrophysical clutter, and astrophysical clutter is very committed to being inconvenient. Freeze out also gives us a way to understand why WIMPs would not form ordinary objects. After they are left behind, they do not behave like gas made of atoms. Ordinary gas can collide with itself, radiate energy, cool, and fall inward into dense structures. WIMPs mostly pass through one another and through ordinary matter. They can clump gravitationally, but they cannot easily lose energy in the way ordinary gas does. So instead of collapsing into dark planets or dark stars, they form large diffuse halos. These halos are not solid structures. They are more like vast swarms of particles moving in the gravitational field of a galaxy. They are spread out, extended, and difficult to define at the edges. The visible galaxy sits within them, bright and thin compared with the larger dark distribution. This is one reason dark matter feels so strange. If there is so much of it, why is there not a dark chair next to your ordinary chair, or a dark mountain beside the ordinary one? The answer is interaction. To make compact objects, matter needs to shed energy. It needs collisions, radiation, friction, or some other way to settle down. Ordinary matter does this beautifully. Dark matter, at least in the WIMP picture, does not. It remains more like a cloud of motion than a collection of objects. It gathers under gravity but does not cool into the familiar shapes of everyday matter. So it can dominate the mass of a galaxy while making no dark furniture at all, which is probably for the best. One can barely manage the ordinary furniture. There is another subtle point. The freeze-out abundance depends not only on the mass of the WIMP, but also on how likely it is to annihilate. In simple models, the right amount of dark matter comes from a certain balance. Too much interaction, and the WIMPs annihilate too efficiently, leaving too little dark matter, too little interaction, and too many survive. This made WIMPs testable, because the same interaction that helped determine their abundance could also allow detection today. If a WIMP can annihilate in the early universe, perhaps it can scatter off a nucleus in a detector. If it can connect to ordinary particles in one setting, perhaps it leaves clues in another. The details vary by theory, but the general hope was that cosmology, direct detection, indirect detection, and colliders were all looking at different faces of the same hidden particle. That hope has driven an enormous amount of work. Experiments deep underground search for nuclear recoils from WIMPs passing through detectors. Telescopes search for possible annihilation products in space. Colliders search for invisible particles produced in high-energy collisions. Cosmological observations constrain how dark matter behaves and how much of it exists. Each method has strengths and weaknesses. Direct detection depends on WIMPs interacting with ordinary nuclei often enough to be seen. Indirect detection depends on WIMPs annihilating today at detectable rates and in recognizable places. Colliders depend on the WIMP being within reach of human-made collision energies and interacting in ways that produce visible missing energy patterns. Cosmology sees the gravitational result, but not the particle identity. Together they form a net. The difficulty is that the fish may be very small, very slippery, or perhaps not a fish after all. The absence of a confirmed WIMP signal so far has changed the way physicists talk about the idea. Early enthusiasm was often tied to simple models where WIMPs were expected to show up within reach of experiments. As those experiments improved and still found nothing, the simplest versions became less comfortable. Some possibilities remain open, especially if the WIMP is heavier, lighter, more weakly interacting, or more complicated than the classic picture. But the search has widened. Physicists now think about many other dark matter candidates with renewed energy. That does not erase the freeze-out story. It remains a beautiful and important possibility. It simply means nature has not yet told us whether that possibility is real. This is a useful place to remember that a good scientific story can be valuable even before it is confirmed, and sometimes even if it is not the final answer. The WIMP freeze-out picture taught physicists how to connect dark matter abundance to early universe particle interactions. It guided experiments, it sharpened questions, it gave a framework for testing ideas. Even if dark matter turns out to be something else, the logic of freeze-out will remain part of the history of how we learn to think about invisible matter. Science does not only advance by finding the correct answer immediately, it advances by building clear possibilities and letting evidence press against them. Still, the freeze-out idea has a quiet charm that is hard to resist. Imagine the young universe expanding, cooling, thinning out. WIMPs, once common in the particle crowd, begin to disappear as creation becomes difficult, and annihilation continues. Then, gradually, the crowd becomes too sparse. The remaining WIMPs no longer find one another often enough. Their number stops changing significantly. They drift onward. The universe becomes older. Atomic nuclei form. Light eventually travels freely. Gravity gathers dark matter into halos. Gas falls into those halos. Stars ignite. Galaxies turn. Planets form. Billions of years pass. A small rocky world develops oceans, life, mines, and eventually instruments buried beneath mountains, built to catch one of those ancient particles in the act of touching ordinary matter for the briefest moment. That is a long story for something called weak. If WIMPs fill the darkness through freeze-out, then dark matter is not just a missing ingredient. It is a memory of the early universe written in particle abundance. Every dark matter halo would be a kind of archive, preserving information from the time when the universe was hot enough for particles now hidden from us to be made in great numbers. The invisible weight around galaxies would be tied to events far earlier than any galaxy. This is one of the great pleasures of cosmology. It refuses to keep scales separate. The smallest particles and the largest structures keep turning out to be part of the same conversation. A particle interaction too tiny to see can influence how galaxies form. A telescope image of a galaxy can hint at physics from the first moments of time. Of course, we should not speak as though the WIMP freeze-out story has been proven. It has not. The dark matter particle has not been directly identified. Freeze-out is one plausible mechanism, not the only one. Other candidates may arise in different ways. Some dark matter might be produced without ever being in thermal equilibrium. Some could be extremely light fields. Some could belong to hidden sectors with their own interactions. Some could have histories more complicated than the classic WIMP picture. The universe has a habit of being more inventive than our first neat ideas, but the WIMP freeze-out remains one of the clearest examples of how a particle from the early universe could naturally become the dark matter we infer today. The process also shows why the WIMP is not merely a particle that ignores matter. It ignores matter now because the universe is cold, spacious and quiet compared with its beginning. But in the early universe, even a weakly interacting particle was part of a dense environment where encounters mattered. Its present silence may be the aftermath of a very busy youth. That is almost relatable in a cosmic way. Once surrounded by constant activity, now drifting mostly alone through the dark, rarely meeting anyone, occasionally passing through a planet without stopping. If particles could reminisce, a WIMP might remember the early universe as a very crowded party that ended nearly 14 billion years ago. What makes this story especially relevant for the search is that freeze-out leaves expectations. If WIMPs have the interaction strength needed to produce the right relic abundance, then perhaps they should not be completely beyond detection. This was the promise. The same quiet handshake that determined their survival might be rare but measurable. Underground detectors were built with this in mind. If dark matter is passing through Earth, and if it can weakly scatter off nuclei, then enough detector mass and enough time might reveal the occasional collision. The search is difficult, because the signal is small and backgrounds are stubborn, but the logic is direct. If the darkness is filled with relic WIMPs, then every laboratory on Earth is moving through a dark matter sea. Earth does not sit still in that sea. The Sun moves around the centre of the Milky Way, and Earth moves around the Sun. This means our motion through the dark matter halo should vary slightly over the year. Some experiments have looked for seasonal changes in possible detection rates. A true dark matter signal might rise and fall in a predictable annual pattern. The idea is elegant, though interpreting such signals is hard because ordinary backgrounds can also vary. Still, it adds another layer to the image. We're not simply waiting for WIMPs to come to us. We are sailing through the galactic halo, carried by the motion of the Sun, while Earth turns and orbits and detectors quietly count. The phrase "filled the darkness" should not be taken to mean WIMPs fill every place equally. Dark matter density varies. It is higher in halos, lower in cosmic voids, shaped by gravity over time. But compared with ordinary matter, it is spread very broadly. Around a galaxy, the WIMP population would extend far beyond the visible disk. In the spaces between stars where ordinary matter may be extremely thin, dark matter may still be present as part of the halo. It does not make the darkness glow. It does not make the vacuum thick in any everyday sense. It simply contributes mass, quietly, cumulatively, with no need to be seen. There is a calming strangeness in that. The dark spaces between stars may not be empty in the way our eyes suggest. They may be crossed constantly by particles older than starlight, particles that once belonged to the hot young universe and now drift through the quiet architecture of galaxies. They do not carry messages. They do not form atoms. They do not make sound. They may almost never touch anything. Yet their collective gravity could be one of the reasons galaxies exist as they do. The universe once again reminds us that visibility is not the same as importance, and so the WIMP freeze-out story brings together several parts of the mystery. The weak force explains how a particle can interact rarely. Mass explains how it can contribute to gravity. Stability explains how it can survive. The early hot universe explains how it could be made. Expansion and cooling explain how a leftover abundance could remain. Gravity explains how that abundance could gather into halos. The modern detector explains how we might still hope to catch one rare interaction today. Each piece connects to the next without needing the particle to be bright, familiar, or easy. The WIMP is a candidate built from restraint. It does very little. But if there are enough of them, and if they have been doing very little for almost the entire age of the universe, that may be enough to shape the cosmos. From that early cosmic leaving behind, our attention naturally moves to the places where humans try to hear the result. If WIMPs froze out long ago and now drift through the galaxy, then the only way to move from elegant possibility to discovery is to catch them somehow. Not with a net, not with a telescope in the ordinary sense, not with a jar held up to the night sky, but with detectors built to wait for the rarest of touches. These instruments are often placed deep underground, far from the noisy rain of cosmic rays, surrounded by shielding, watched by sensors sensitive to tiny flashes and recoils. They are among the quietest listening posts ever made, temples not to certainty but to patience, where scientists ask whether the ancient dark still remembers how to shake hands with ordinary matter. Far below the ordinary noises of the world, beneath roads, trees, weather, birdsong, passing trucks, and people carrying on with the urgent business of lunch, there are rooms built for waiting. They are not waiting for earthquakes, or treasure, or messages from lost civilizations, though they can feel a little like all three if you let your imagination stretch. They're waiting for a particle that may have crossed the galaxy without touching anything, slipped through the atmosphere without slowing, passed into the rock as though the rock were no more substantial than mist, and finally, by a chance so small it almost sounds impolite, nudged an atom inside a detector. That tiny nudge, if it happened, could be the first direct greeting from dark matter. Not a grand announcement, not a flash across the sky, just the faintest disturbance in a carefully prepared silence. This is why dark matter detectors are so often built underground. The surface of Earth is not quiet, not in the way particle physicists need it to be quiet. Even when a landscape seems still, invisible particles from space are constantly arriving. Cosmic rays strike the upper atmosphere and produce showers of secondary particles, some of which reach the ground. Natural radioactivity exists in rocks, soil, building materials, metals, dust, and even in the human body. The world is full of tiny particle events. To us, this does not matter most of the time. We do not walk around feeling cosmic rays tapping our shoulders, and we are very fortunate that the ordinary background is usually harmless. But for an experiment trying to hear one rare dark matter interaction, this background is like trying to hear a single whisper in a room where everyone is politely but continuously clearing their throat. So scientists go down. They place detectors deep in mines, tunnels, mountain laboratories, and underground caverns where huge amounts of rock act as shielding. The rock does not stop everything, but it reduces the rain of cosmic particles from above. It turns the volume down. A detector that would be overwhelmed at the surface can become more useful underground, not because dark matter prefers caves, but because ordinary noise is quieter there. WIMPs, if they exist, would pass through the overlying rock almost as easily as through air. They would not mind the mountain. Cosmic ray particles, however, are much more likely to be blocked or reduced. In this sense, the underground laboratory is not hiding from dark matter. It is hiding from everything else. There is something almost monastic about these places. Not because the scientists wear robes or chant over liquid xenon, though one suspects a few exhausted graduate students have muttered things into the dark that sounded ancient and ceremonial. It is monastic because the whole purpose is discipline, patience, and quiet. The detectors are built inside layers of protection. The materials are chosen carefully, cleaned carefully, tested carefully. The air is controlled, dust is treated as an enemy. The surrounding rock is measured for radioactivity. Every cable, bolt, sensor, and seal may be examined because even a tiny impurity can create a background signal. Ordinary matter is not just the target in these experiments, it is also the troublemaker. That is one of the strange challenges. To detect a WIMP, you need ordinary matter because the WIMP must strike something. But ordinary matter is full of its own little radioactive habits. Some atoms are unstable. Some materials contain trace elements that decay over time. These decays can create flashes, heat, or particle tracks that look suspiciously like the kind of signal researchers are seeking. The detector must therefore contain enough matter to give a passing WIMP a reasonable chance of interaction, while being so pure and so well understood that ordinary events can be recognized and rejected. It is a little like trying to catch a ghost by filling a room with bells, then discovering that every bell also rings faintly on its own whenever the pipes settle. Different experiments choose different kinds of bells. Some use liquid xenon, a heavy noble element that can be cooled until it becomes a dense liquid. Xenon is useful because its atoms are heavy, its behaviour in detectors is well studied, and when a particle strikes one of its nuclei, it can produce both light and freed electric charge. These two signals together help researchers determine what kind of event occurred. A WIMP, if it scattered off a xenon nucleus, would produce a nuclear recoil, meaning the nucleus would be kicked slightly. Other particles, such as those from ordinary radioactive backgrounds, often interact more with electrons. By comparing the signals, scientists can separate possible dark matter events from many kinds of background. Not perfectly. Nothing in this business is perfect, but well enough to make the search meaningful. A xenon detector is not just a bucket of cold liquid. Though that would be a wonderfully simple grant proposal, it is an intricate instrument. The liquid must be purified so that light and charge can travel through it without being absorbed too quickly. Sensors must detect tiny flashes. Electric fields must guide freed electrons through the detector. The whole system must be kept stable, cold, clean, and shielded. Around it may be layers of water, metal, plastic, or other materials designed to block radiation and identify unwanted particles. Every component has a purpose. Every component can also become a source of background if it is not chosen carefully. Building such a detector is like building a musical instrument that must play only when the universe touches it in exactly the right way. Other experiments use liquid argon, another noble element with useful detection properties. Argon can produce bright signals when particles interact inside it, and it can be obtained in large quantities. But argon also has radioactive isotopes that must be considered, so some experiments use argon sourced from underground, where it has been shielded from cosmic ray production for long periods. That detail gives a sense of how precise the work becomes. It is not enough to say, we need argon. The question becomes, what kind of argon? From where? With what history? Containing what tiny traces of what unwanted atoms? The detector is not only a machine, it is a biography of materials. Some detectors use crystals cooled to extremely low temperatures. In these experiments, a particle interaction can produce a tiny rise in heat, so small that it would be impossible to notice unless the crystal were already held near an extraordinarily cold state. At such low temperatures, even a small deposited energy can stand out. Other detectors look for ionization or for scintillation, a flash of light produced when particles pass through certain materials. Some use germanium, some use sodium iodide, some combine signals in clever ways. Each approach is a different strategy for the same basic question. Did a dark matter particle just touch this ordinary matter, or was that signal made by something else? This question is harder than it sounds because WIMP signals are expected to be rare and modest. A dark matter particle would not smash through the detector like a bowling ball through a shop window. It would transfer only a small amount of energy to a nucleus. The nucleus would recoil, and the detector would record a tiny event. The difficulty is that many other things can also produce tiny events. Neutrons are especially troublesome because they can strike nuclei in a way that resembles a WIMP. A neutron does not carry electric charge, so it can penetrate shielding more easily than many charged particles, and when it hits a nucleus, it can create the same kind of recoil that dark matter might create. For this reason, neutron backgrounds are studied with great care. If WIMPs are shy guests, neutrons are the mischievous relatives who keep signing the guestbook under the wrong name. Scientists use several methods to reject backgrounds. They shield the detector, they place it underground, they use veto systems, which are surrounding detectors that identify particles entering from outside. They choose materials with extremely low radioactivity. They analyze the shape, timing, and location of events. If a signal occurs near the edge of the detector, it may be more likely to come from background entering from the outside. If multiple interactions happen close together, that may suggest an ordinary particle passing through, because WIMPs are expected to interact at most once as they cross a detector. A true WIMP event would likely be a single, isolated nuclear recoil in the quiet central region of the target. One small note in the middle of silence. Even the central region of a detector is carefully defined. In large liquid noble detectors, researchers often use the outer part of the detector as shielding for the inner part. The cleanest search region is inside, away from the walls, away from surfaces, away from materials that may produce background. This inner region is sometimes called the fiducial volume, which is a rather official-sounding phrase for the part of the detector scientists trust most. It is not that the rest of the detector is useless. It helps protect and understand the inner region, but the central volume is where the search becomes most sensitive. It is the quietest seat in the quietest room. The scale of these experiments can be surprising. Some contain tons of detector material, which sounds enormous until you remember how rarely WIMPs may interact. If dark matter passes through Earth continuously, why need so much material? Because almost all of it passes through without touching anything. The more target material you have, the more chances you offer. The longer you wait, the more chances accumulate. Dark matter detection is therefore a game of mass, time, quiet, and patience. A small detector may be elegant, but if the interaction is rare enough, you need something large. A large detector may be powerful, but if it is noisy, it becomes confusing. The ideal experiment is big, clean, quiet, stable, and watched for a long time. In other words, a very expensive form of listening. There is a human side to this patience. Behind every underground detector are teams of people who design, weld, clean, calibrate, simulate, test, troubleshoot, and worry. They lower delicate instruments into deep spaces. They check pumps and cables. They monitor temperatures and pressures. They write software to distinguish signal from background. They hold meetings where the phrase "maybe it is just background" can hover over the room like a small grey cloud. They blind their analyses so that they do not fool themselves by seeing what they hope to see. Blinding means hiding certain parts of the data or the final signal region during the development of the analysis, so choices are not biased by knowledge of the possible result. It is a scientific act of humility. The researchers know that humans are very good at persuading themselves, so they build procedures that make persuasion harder. This is especially important in dark matter searches because the desired signal is so subtle and so valuable. A false discovery would be damaging. A real discovery would be historic. When the stakes are like that, caution becomes part of the instrument. It is not enough to build sensitive hardware. One must also build careful habits of thought. A possible event must survive background estimates, calibration checks, statistical tests, comparisons with other experiments, and the slow skepticism of a community trained to ask, "Are you sure?" That question may sound discouraging, but it is one of the most useful questions science has. It keeps the universe from being replaced by wishful thinking. Underground laboratories often host more than dark matter experiments. They may house neutrino detectors, studies of rare nuclear processes, and other experiments that require low background conditions. The same underground quiet useful for WIMPs is useful for many rare event searches. These places become scientific shelters from the noisy surface world, not isolated from society but insulated from particles. There is a pleasing contrast in that. Above ground, weather changes, markets open, phones ring, people rush through train stations, and dogs continue to believe every passing bicycle is a matter of national importance. Below ground, a detector sits in cold darkness, waiting for a signal that may happen once in a very long while, if at all. Water is often part of the protection. Large tanks of water can shield detectors from radiation, and they can also reveal incoming particles through flashes of light produced when fast particles pass through. The water must be purified. The tank must be lined and instrumented. The detector inside must be isolated but accessible. From the outside, it may look like engineering. From the inside, conceptually, it is almost an artificial cave within a cave, a quiet pool guarding an even quieter heart. The layers matter because each unwanted particle stopped or identified is one less false whisper in the dark. Calibration is another essential part of the work. A detector cannot simply wait and then interpret any small signal as dark matter. Scientists must understand how the detector responds to known sources. They expose it carefully and safely to particles or radiation with known properties, then measure the resulting signals. They build maps of detector response. They learn how light travels through the target, how charge is collected, how signals vary by location and energy. They model the backgrounds. They test the electronics. Only by understanding ordinary events can they recognize something extraordinary. A detector is not a magic box. It is a question asked in hardware, and calibration teaches researchers the language in which the box answers. Sometimes the answer is silence. In fact, most of the time, so far, the answer has been silence. Experiments have become more sensitive, and many have reported no convincing WIMP signal. This silence is not nothing. It tells us that if WIMPs exist in the tested ranges, they interact with ordinary matter less often than earlier experiments could have seen. Each non-detection tightens the limits. The allowed hiding places become smaller or stranger. A detector that sees no WIMPs may still produce an important result because it rules out models that predicted signals above its sensitivity. In dark matter research, a quiet result can be a loud message to theory, but silence can also be complicated. Different experiments use different materials, methods, thresholds, and assumptions. A possible signal in one experiment must be checked against the absence of signals in others. If one detector sees an annual variation, for example, but other detectors with different target materials do not see compatible evidence, interpretation becomes difficult. Is it dark matter interacting in an unexpected way? Is it a background not fully understood? Is it something related to the environment, the detector, or the analysis? These are not easy questions, and they are why the field proceeds cautiously. A single strange result is interesting. A consistent pattern across methods is far more convincing. The dream, of course, is a clear detection. Imagine a signal appearing with the right features, in the right region, with backgrounds understood, and then being confirmed by other experiments using different targets. Imagine the rate matching the expected motion of Earth through the galaxy. Imagine collider searches or indirect observations adding supporting clues. That would be extraordinary. It would not merely identify a new particle, it would connect the underground laboratory to the rotation of galaxies, to the early universe, to the invisible majority of matter. A tiny recoil inside a detector could become a bridge from the smallest measured disturbance to the largest cosmic structures. That is why people keep building these instruments. The prize is not a number on a chart. It is a new understanding of what the universe is made of. Still, the detectors must face a looming difficulty sometimes called the neutrino background. Neutrinos, especially from the Sun and from cosmic sources, can produce signals that resemble dark matter interactions. As detectors become more sensitive, they begin to encounter neutrinos as an unavoidable background. This does not make dark matter detection impossible, but it makes the search harder. Neutrinos are real, abundant and weakly interacting, and they have every right to pass through the detector too. They are like nature reminding physicists that even when you remove most of the noise, there is another quieter noise underneath. Eventually, distinguishing WIMPs from neutrino events may require direction sensitivity, multiple detector materials, or other clever strategies. The quiet room has layers of quiet, and the deepest layer still has visitors. There is also the possibility that WIMPs are not the answer. The underground temples may be listening for the wrong kind of silence. Dark matter might be lighter than classic WIMPs, requiring different detector technologies. It might interact through hidden forces, or exist as waves rather than particles in the usual sense. It might have properties that make ordinary WIMP searches less effective. This does not make underground detectors foolish. It makes them part of a broader exploration. You do not know which door hides the answer until you try opening doors, and sometimes finding that a door is locked teaches you that the hallway is shaped differently than you thought. The word temple is not scientific, but it fits the mood if used gently. These underground spaces are built for attention. They are places where human beings arrange matter with extreme care in order to ask a question that ordinary life cannot answer. They are not temples to belief, because belief is not enough. They are temples to measurement. They contain doubt, procedure, patience, and engineering. They are designed around the possibility that the universe may speak in a signal so small that only a deeply disciplined instrument can hear it. There is humility in that design. Scientists do not demand that dark matter reveal itself dramatically. They make a quiet place and wait for whatever nature permits. The detectors also remind us that seeing is not the only way to know. Dark matter, by definition, does not present itself through ordinary light, so we build other senses. A detector can feel a recoil too small for any human body to feel. It can notice a flash of light from a single particle event. It can collect a few electrons and reconstruct where an interaction happened. It can distinguish a nuclear recoil from an electronic one with statistical care. These instruments extend our senses into realms where intuition has no reach. They are artificial nerves for the invisible, and if a WIMP passes through without interacting, which almost all would, nothing happens. That is perhaps the strangest part. The detector is not failing when most WIMPs pass through. That is exactly what WIMPs are expected to do. The experiment is built around rare exceptions. It is not trying to stop the dark matter wind. It is trying to catch one grain of it brushing against the right atom. This is why the whole enterprise feels so delicate. The galaxy may be full of dark matter, but abundance does not guarantee contact. The hidden sea flows through the net because the net is made of ordinary interactions, and WIMPs are very good at ignoring ordinary interactions. The underground search is therefore a kind of negotiation with probability. Increase the mass, increase the time, decrease the background, improve the sensors, understand the materials, compare the data, wait. Each improvement gives nature less room to hide in that particular way. Perhaps one day a signal appears. Perhaps the silence continues and the classic WIMP retreats further from favour. Either outcome teaches us something. Discovery would be magnificent. Exclusion is still knowledge. Science often advances not by being handed answers, but by patiently removing wrong possibilities until the right one has fewer places to avoid us. So beneath the surface, in caverns and mines and mountain halls, the search continues in darkness that is not empty and silence that is not passive. The detectors wait inside shields, inside rock, inside careful assumptions, watching for the smallest sign that dark matter is not only gravitationally real, but particle real in the way WIMPs propose. Above them, people sleep, cook, argue, commute, fall in love, lose umbrellas, and look up at the stars. Below them, a tank of liquid xenon or argon, a crystal chilled almost beyond ordinary imagination, or another carefully prepared target listens for a touch from the ancient universe. The WIMP, if it exists, does not know it is being hunted. It does not know it has been named. It does not know that theories, careers, detectors, and late-night coffees have gathered around its possible existence. It simply moves through the galaxy, through stone, through instruments, through us, almost always saying nothing. And after all this patient listening, after years of deeper laboratories, cleaner materials, larger targets, and sharper analyses, the story becomes more complicated. The silence itself begins to speak. The WIMP remains possible, but not as comfortably as it once did. Experiments have searched in places where many hoped it would appear, and the particle has not stepped into the light, or rather, into the carefully measured darkness. The hunt has not ended, but it has changed. Hope has become more disciplined. Questions have become sharper. The simple picture has been pressed hard by data, and the next turn in the story is not merely about how we search, but about what it means when the universe keeps refusing to answer in the way we expected. By the time the search for WIMPs became a serious experimental quest, the idea had gathered a very particular kind of hope around it. Not the careless kind of hope, where one simply wishes the universe will be convenient, but the disciplined hope that comes from several clues seeming to lean in the same direction. Galaxies behaved as though they were held by invisible mass. The early universe seemed to require a non-ordinary matter component. Particle physics had reasons to suspect that undiscovered massive particles might exist. The weak force offered a way for such a particle to be hidden, but not completely unreachable. The freeze-out story suggested that a relic population of WIMPs could naturally survive from the early cosmos in roughly the right abundance. Put all of that together, and the WIMP began to look less like a random guess, and more like a well-dressed suspect standing quietly near the scene, not confessing, but also not leaving. For several decades, this made the WIMP one of the most popular candidates for dark matter. It had the useful quality of being mysterious but testable. That is a rare and valuable combination. Some ideas are easy to imagine but almost impossible to check. Others are measurable, but not especially deep. The WIMP sat in the attractive middle. If it existed, perhaps we could catch it in an underground detector. If it was produced in particle collisions, perhaps a collider could create it. If WIMPs gathered densely enough in space and occasionally annihilated, perhaps telescopes could see the byproducts. The same particle might leave traces in 3 very different places, beneath mountains, inside accelerators, and across the sky. That gave the hunt a sense of convergence. It felt as though nature had left several doors slightly ajar, and physicists, very carefully, began trying each handle. The direct detection approach was the most literal. If the galaxy is filled with WIMPs, and if Earth is moving through that dark matter halo, then WIMPs should pass through laboratories all the time. Almost all would pass through without doing anything. But every so often one might strike the nucleus of an atom inside a detector. That strike would make the nucleus recoil, leaving a tiny signal. This is the quiet handshake we have been circling around. Not a bright flash visible to the eye, not a dramatic burst of energy, but a delicate event hidden among many possible backgrounds. To search for it, experimenters built detectors that became larger, cleaner, colder, deeper, and more sensitive. They used liquid xenon, liquid argon, chilled crystals, and other carefully chosen materials. They pushed the world of measurement toward the faintest edge of possibility. At the same time, indirect detection searched the universe for signs that WIMPs might destroy each other in places where dark matter is dense. The centre of the Milky Way, dwarf galaxies orbiting our own galaxy, galaxy clusters, and even the Sun became possible hunting grounds depending on the model. If WIMPs met and annihilated, they might produce ordinary particles or radiation. Telescopes could then look for unusual signals, but space is not a quiet laboratory. It is full of astrophysical engines. Pulsars spin, black holes feed, supernova remnants accelerate particles. Gas clouds glow. Cosmic rays collide with interstellar material. A suspicious signal from space must therefore pass a difficult test. It must not only appear, it must appear in a way that ordinary astrophysics cannot explain better. The universe is very good at offering alternative explanations, rather like a cat found beside a broken vase, with an expression of deep professional innocence. Colliders offered a third route. If WIMPs could be created in high-energy particle collisions, then machines like the Large Hadron Collider might produce them. A WIMP would not be seen directly inside the detector, because it would escape without interacting much. Instead, scientists would look for missing energy, a sign that something invisible carried energy away from the collision. But this search is also subtle. Known particles such as neutrinos can escape detectors too, and many processes can create complicated patterns. Collider searches depend strongly on how the WIMP connects to ordinary particles, how heavy it is, and what other particles might exist with it. So a collider can close certain doors, but not the whole mansion. If nothing appears, it may mean that WIMPs are too heavy, too weakly connected, or simply not the kind of particle the collider can make. For a while, many people hoped that these methods would meet in the middle. Perhaps an underground detector would see a signal. Then a collider might produce an invisible particle with related properties. Then telescopes might find a matching signal from dark matter-rich regions. A picture would form from several angles, each method checking the others. This is the dream of particle astrophysics, to connect the cosmic and the microscopic so tightly that the same hidden particle can be recognized in a galaxy, a detector, and a collision. It is a beautiful dream because it would turn dark matter from an inferred gravitational substance into a known part of nature. We would stop saying something seems to be there and begin saying this is what it is. But the story did not unfold that simply. The detectors listened, and mostly they heard no WIMP. Colliders searched, and no clear WIMP candidate appeared. Telescopes found interesting signals here and there, as telescopes often do, but none became the unmistakable dark matter signature everyone could agree on. The Great WIMP Hunt entered an era of silence. Not complete silence, because the experiments produced data, limits, methods, technologies, and important discoveries about backgrounds. But silence in the sense that the expected guest did not arrive. The WIMP did not knock loudly enough. The simplest versions of the idea began to feel less comfortable. This silence is not the same as failure. That is important. In science, a null result is still a result. If an experiment is sensitive enough to detect a certain kind of WIMP and finds nothing, then that kind of WIMP is less likely, sometimes ruled out in a strong way. The search area shrinks. The possible properties of the particle are constrained. Theories that once seemed plausible become harder to maintain. A detector that sees nothing may still have asked nature a clear question and received a clear answer. Not there, not like that, not at that strength. It is not as exciting as a discovery announcement, but it is still knowledge. It is the universe drawing boundaries around our guesses. Physicists often speak of excluding regions of possibility. That may sound dry, but it is really a map being drawn in the dark. Imagine searching for a very quiet animal in an enormous forest. You place sensitive microphones in one valley and hear nothing. That does not prove the animal does not exist, but it tells you it is probably not calling loudly from that valley. You place cameras near a river and see nothing. It may not visit that river, or it may move at another time, or it may be smaller than expected, or perhaps the animal is not real. Each attempt changes the map. The empty places matter. Over time, the search becomes more focused or sometimes more unsettling, because the places where the original idea could comfortably hide become fewer. For the WIMP, this has meant that many simple models have been squeezed. A classic WIMP with interaction rates once considered likely should have shown itself in some experiments by now. Since it has not, physicists have had to ask harder questions. Maybe WIMPs interact even more weakly than expected. Maybe their mass is outside the most searched ranges. Maybe they interact differently with protons and neutrons. Maybe they prefer some materials over others. Maybe they belong to a more complicated dark sector, with hidden forces and particles. Maybe the dark matter is not a WIMP at all. Each possibility keeps the conversation alive, but it also makes the old simple story less neat. The WIMP has not been eliminated, but it has become a more elusive suspect. This is a very normal pattern in physics. A beautiful, simple idea appears. Experiments test the simplest version. If nature agrees, everyone celebrates, and then immediately begins arguing over details. If nature does not agree, the idea either changes, retreats, or is replaced. The difficult part is knowing when an idea is still worth pursuing and when it has become too flexible. If a theory can adapt to any result, it may stop being useful. But if a theory still makes clear predictions in unexplored regions, it remains scientific. The WIMP is in this more complicated territory. Some forms remain testable and interesting. Others have been strongly disfavoured. The field has not abandoned the WIMP, but it no longer treats the classic version as the obvious answer waiting just around the next experimental corner. The emotional tone of this search is unusual. There is hope, because dark matter is real as a gravitational problem and WIMPs remain plausible in some forms. There is silence, because the major searches have not produced a confirmed detection. And there are new questions, because silence forces imagination to widen. When a detector does not see what it was designed to see, scientists do not simply shrug and go home, though they may briefly stare into a coffee cup with unusual intensity. They ask what else could be true. Could dark matter be lighter? Could it be heavier? Could it interact through a force not included in the simplest models? Could it have a rich hidden world of its own? Could there be more than one kind of dark matter? Could the particle be so light that it behaves more like a field than a tiny billiard ball? Could it be something we have not named yet? This widening search is one of the healthy outcomes of the WIMP era. The WIMP gave dark matter research a strong experimental program. As that program pushed deeper and did not find the expected signal, it opened space for other candidates. Axions gained renewed attention. Light dark matter models became more active. Hidden sector ideas grew. Primordial black holes remained debated in specific ranges. Modified gravity theories continued to be studied, though they faced challenges in explaining the full range of evidence. The landscape became broader. That does not mean the WIMP was a mistake. It means the WIMP was a powerful starting point, and nature may be asking for a wider vocabulary. The underground experiments themselves have not stood still. They have become larger and more sensitive. A modern dark matter detector may contain several tons of target material, surrounded by shielding and sensors, operated with extraordinary care. Researchers understand backgrounds better than ever. They can distinguish many types of events with great precision. They can reject signals from ordinary radioactivity, cosmic rays, and neutrons more effectively than earlier experiments. This progress is impressive even without a WIMP discovery. It has pushed technology and analysis into regimes of remarkable subtlety. It has also brought the field closer to an unavoidable background from neutrinos. Neutrinos are both a triumph and a nuisance. They prove that weakly interacting particles can be real and detectable with enough patience. But they also produce signals that can resemble dark matter. Solar neutrinos, atmospheric neutrinos, and other neutrino sources can interact in detectors and create nuclear recoils. As dark matter detectors improve, they become sensitive enough that neutrinos are no longer just a distant concern. They become part of the background. This creates a natural difficulty. At some point, distinguishing WIMPs from neutrinos may require more information than a simple recoil signal provides. Directional detection, multiple target materials or new methods may help. The search reaches a point where the quietest known particles begin to imitate the unknown ones. Nature has a dry sense of humour. This neutrino background does not close the search. It changes the search. If a WIMP signal is strong enough or has the right features, it could still be found. But the easy part of the search, if there was ever an easy part, is gone. The next advances may require detectors that can tell not only that a nucleus recoiled, but perhaps which direction the recoil came from. If dark matter flows through the solar neighbourhood in a broad galactic pattern, its direction should differ from neutrino sources like the Sun. Directional detectors would be extremely valuable, but they are technically challenging. A dark matter particle does not leave a neat glowing arrow saying "this way please." The recoil is tiny, and reconstructing its direction is a difficult art. Indirect searches face their own version of ambiguity. Over the years, some signals have stirred excitement. Certain excesses in gamma rays, cosmic rays, or other messengers have been discussed as possible hints of dark matter. But astrophysics is crowded with possible explanations. Pulsars, gas modelling, cosmic ray propagation, and unresolved sources can all complicate interpretation. A real dark matter signal would need to survive this crowd. It would need to appear with the right spatial pattern, energy behaviour, and consistency across targets. Dwarf galaxies are especially useful because they are thought to be rich in dark matter and relatively quiet in ordinary astrophysical activity. Yet even there, the signal has not become decisive. The sky continues to offer hints, puzzles, and caution, but not yet a clear WIMP signature. At colliders, the story has also been sobering. The Large Hadron Collider has discovered the Higgs boson, a major triumph for particle physics, but it has not found the kind of new particle zoo that some theories predicted. Simple supersymmetric models, once among the most famous sources of WIMP candidates, have been pushed into more constrained territory. Supersymmetry itself is not entirely ruled out, especially in more complex forms, but the early expectation of easily found partner particles has not been fulfilled. This matters for WIMPs because some of the most beloved WIMP candidates came from these frameworks. The missing collider evidence does not kill all WIMPs, but it removes some of the theoretical comfort that once surrounded them. The result is a field in a thoughtful state. Not defeated, not aimless, but less certain. The old confidence has been replaced by a more mature kind of curiosity. Scientists are still building and planning WIMP searches, but they are also exploring alternatives with increasing seriousness. The dark matter problem is too strong to ignore, and the WIMP idea remains too plausible in some forms to discard completely. Yet the silence has taught everyone to be cautious. A good theory must be loved lightly enough that it can be questioned. The universe is not a student taking our exam. We are the ones being examined. This is where the word hope changes meaning. Early hope may have sounded like expectation. The WIMP should be there. The next detector may find it. The collider may produce it. The signal may be just around the corner. Later hope becomes more patient and less demanding. It says the search is worthwhile because the question is profound, because each result teaches us something, because dark matter remains unexplained, and because nature has surprised us before. It does not require the WIMP to appear on schedule. It allows for the possibility that the answer is stranger than expected. This is a healthier hope, less like waiting for a bus at a timetable, and more like exploring a coastline whose shape no map has fully captured. The silence also forces a useful distinction between evidence for dark matter and evidence for WIMPs. The evidence for dark matter as a gravitational phenomenon remains strong. Galaxy rotation, gravitational lensing, clusters, cosmic structure, and the early universe all continue to point toward missing non-ordinary mass in the standard picture. The evidence for WIMPs specifically is different. WIMPs are one proposed identity for that mass. The failure to find WIMP so far does not make the galaxy rotation problem vanish. It does not remove the lensing evidence. It does not erase the cosmic background patterns. It only tells us that the dark matter, if it is particle dark matter, may not be the simplest WIMP. Keeping those ideas separate prevents confusion. The mystery remains even if one candidate struggles. There is a lesson here about how science handles the unseen. When something invisible is inferred, skeptics rightly ask whether the inference is sound. Scientists then test every part of the argument. Could the mass be ordinary matter? Could the measurements be wrong? Could gravity behave differently? Could another particle explain it better? Could the experiments be missing something? This process can look messy from the outside because scientists argue, revise, rule out, resurrect, and rename ideas. But the mess is part of the strength. Dark matter research is not a single belief. It is a network of measurements, models, tests, and competing possibilities. The WIMP hunt is one path through that network, a path that began with strong motivation and now continues with more caution. It is tempting in a story like this to make silence dramatic, as though every null result is a door slamming shut in a dark hallway. But real scientific silence is usually quieter than that. It arrives in plots, data tables, calibration reports, background models, and careful statements. It says that under these assumptions in this mass range for this interaction type, the particle has not been observed. It is not a theatrical no, it is a measured no. And enough measured no answers can reshape a field. They do not shout, they accumulate. They are the scientific version of a room slowly becoming smaller around a hiding place. For people outside physics, this can be frustrating. After all, if dark matter is supposed to make up so much of the universe, why is it so hard to find? The answer is that amount and detectability are not the same. The galaxy may contain enormous dark matter mass overall, but any individual particle may interact so rarely that a detector can wait a long time and see nothing. Imagine a rainstorm made of drops that pass through roofs, floors, buckets, and hands almost every time, with only one drop in an unimaginable number leaving a mark. You could stand in that storm and remain dry. That is the WIMP problem in everyday terms, although the actual physics is more precise and much less useful for weather forecasts. The new questions have also led to new detector ideas. If dark matter is lighter than classic WIMPs, it may not kick nuclei hard enough for traditional detectors to notice. Then scientists might look for interactions with electrons, tiny vibrations in crystals, changes in superconductors, or other delicate effects. If dark matter behaves more like a wave, different instruments are needed altogether. If it interacts through hidden photons or other new mediators, experiments can be designed to search for those connections. The field has become more creative because the old silence made creativity necessary. In that sense, the WIMP hunt has not narrowed physics into disappointment. It has opened a wider experimental imagination. Even so, the WIMP remains present in the story, like a character who has left the room but whose coat is still on the chair. The idea still has viable forms. Future detectors may probe deeper. More data may reveal a signal. A new theoretical development may show that WIMPs were hiding in a less obvious way. Or the WIMP may gradually fade as other candidates gain strength. It is too early to speak with finality, and finality is rarely wise in a field where the main object has not yet been identified. The correct attitude is neither blind faith nor dismissal. It is careful attention. There is something almost philosophical, though still very practical, about hunting a particle that refuses to appear. The search tests not only instruments but expectations. It asks whether elegance is a guide to truth. Sometimes it is, sometimes it is not. The WIMP was elegant because it connected particle theory, cosmology and detection in a simple way. But nature may prefer a less tidy solution. The history of science is full of both outcomes. Sometimes the beautiful idea is right. Sometimes the awkward data are pointing toward a deeper beauty that no one has yet learned how to see. The only safe response is to keep measuring. So the Great WIMP Hunt stands as one of the most ambitious listening projects in modern physics. It has sent scientists underground, into space-based observations, into collider tunnels, into simulations of the early universe, and into the delicate mathematics of particle theory. It has produced no confirmed WIMP, but it has produced a sharper dark matter problem. The particle, if it exists, is more hidden than many first hoped. The experiments, if they are to find it, must become more sensitive or more clever. The theories, if they are to explain it, must be more flexible without becoming vague. and the rest of us, listening from comfortable rooms and ordinary beds, can appreciate the strange patience required to ask the universe a question for decades and accept that the answer may arrive first as silence. That silence is not empty. It contains limits, lessons, and a widening sense of possibility. It tells us that dark matter is not easily forced into our favourite shape. It reminds us that the invisible majority of matter, if that is what it is, may be more subtle than the first candidate that captured our imagination. And it leaves us at a fascinating edge. The WIMP may still be hiding, tucked into a difficult range of mass or interaction strength, waiting for the next generation of detectors to notice it. Or it may be that the real dark particle is something else entirely, something lighter, stranger, more hidden, or more surprising than the classic WIMP. Either way, the hunt has brought us closer to the shape of the mystery, and the next question becomes unavoidable. If the WIMP has not yet answered, what if the dark particle is still hiding in a form we have only just begun to imagine? If the WIMP has not yet stepped into the carefully prepared silence, then the next thought is both simple and enormous. Perhaps the dark particle is still hiding. Not hiding with intention, of course. Particles do not crouch behind cosmic furniture, hoping the physicists will give up and go make sandwiches, but hiding in the practical sense, hiding because its properties place it beyond the reach of the instruments we have built so far, hiding because our best guesses have been close enough to be useful but not close enough to be right, hiding because nature may have chosen a darker, quieter, or stranger solution than the one we first imagined. This is not a small possibility. It sits at the centre of modern dark matter research. We have powerful evidence that something unseen shapes galaxies and clusters, bends light, and influenced the growth of structure in the early universe. Yet the identity of that something remains unknown. The WIMP was a brilliant candidate because it connected so many pieces at once. It had mass, it could be stable, it could interact rarely, it could be produced in the early universe, it could leave behind the right kind of cosmic abundance. It could be searched for in underground laboratories, in particle colliders, and through telescopes watching the sky. It was elegant enough to inspire confidence and concrete enough to test. But the tests have been quiet, and quiet tests make scientists ask new questions. One possible answer is that the WIMP is still there, but not where the simplest searchers expected it to be. Perhaps it is heavier than the most accessible versions. A heavier WIMP might be harder to produce in colliders and might leave fewer detectable events in underground experiments, depending on how it interacts. Perhaps it is lighter than expected, so light that traditional detectors looking for nuclear recoils are not well matched to it. If a dark matter particle is too light, it may strike a nucleus but give it only the gentlest nudge, too small for many detectors to notice. In that case, the dark matter could be passing through the instruments, interacting now and then, and still escaping recognition because the signals are below threshold, like someone knocking at a door with a feather. Perhaps the WIMP is not one particle, but part of a larger hidden family. This idea has become increasingly interesting. The ordinary world has many particles and forces. There are electrons, quarks, neutrinos, photons, gluons, and other familiar members of the particle catalogue. There is no rule that says the dark world, if it exists, must contain only one lonely particle standing in the corner. It might have its own structure. It might include several dark particles, perhaps interacting with each other through forces that ordinary matter barely feels. This is often called a hidden sector, though the name makes it sound like a secret department in a very strange office building. The idea is that dark matter may not be simple. It may be part of an unseen realm with its own internal behaviour, mostly disconnected from us except through gravity and perhaps a few tiny bridges. If dark matter has a hidden sector, then the classic WIMP search may be looking for only one kind of connection. The particle may not interact with ordinary nuclei in the way early models assumed. It may prefer electrons. It may interact through a very light mediator, a particle that carries a new dark force. It may scatter only under certain conditions. It may have excited states, meaning it could absorb energy and move into a slightly different internal condition before returning to its original state. It may interact with itself in a way that changes how dark matter behaves inside galaxies. Each of these ideas adds complexity, but not for the sake of decoration. Complexity becomes reasonable when simplicity is pressed by data and does not answer. There is also the possibility that dark matter is much lighter than the WIMP imagined in older searches. A very light dark matter particle would require different detection methods. Instead of looking for a nucleus being kicked, scientists might look for tiny disturbances in electrons, vibrations in crystals, or subtle changes in materials cooled to extreme sensitivity. Some experiments search for dark matter that behaves less like a tiny pellet and more like a wave spread over a region. In that case, the image of a particle drifting through the detector and striking a nucleus may not be the best picture. The dark matter may be more like a faint field surrounding and passing through the experiment, producing tiny oscillations or conversions that require very different instruments. The darkness may not knock, it may hum. One of the most famous alternatives is the axion, a hypothetical particle originally proposed for a different reason in particle physics, but later recognized as a possible dark matter candidate. Axions would be far lighter than typical WIMPs, and they would require detectors built around a completely different strategy. Some experiments use strong magnetic fields and resonant cavities, hoping axions might convert into detectable light under the right conditions. Others search for subtle effects in precision measurements. The axion is not the WIMP wearing a smaller coat. It is a different kind of idea, with a different origin and different experimental language. Its rise in popularity shows how the silence of WIMP searches has widened the dark matter conversation. Another possibility is that dark matter consists of sterile neutrinos. Ordinary neutrinos already show us that weakly interacting particles can be real, abundant, and ghost-like. Sterile neutrinos would be even more elusive in some ways, interacting with ordinary matter even less directly than known neutrinos. They could have masses and behaviours that make them possible dark matter candidates. But they too face observational tests and constraints. Scientists search for signs of their decay, for effects on cosmic structure, and for possible connections to neutrino physics. As with WIMPs, the challenge is to turn a plausible invisible particle into a measured one. There are also primordial black holes, hypothetical black holes formed in the early universe rather than from collapsed stars. These would not be particles in the ordinary sense, but they could behave as dark compact objects. If enough existed in the right mass ranges, they might account for some or perhaps all dark matter. This idea has moved in and out of favour over the years as observations constrain different masses. Too many primordial black holes of certain sizes would produce too many gravitational lensing events, disrupt systems, emit radiation, or leave other detectable traces. Still, some windows remain discussed, and the discovery of gravitational waves from merging black holes has kept interest alive. The dark matter mystery is broad enough that even tiny ancient black holes remain invited to the discussion, though they are watched carefully and not allowed to dominate the conversation without evidence. Then there is the more radical question. What if dark matter is not matter at all? At least not in the particle sense. What if the evidence we interpret as unseen mass is pointing instead toward a modification of gravity on large scales? This idea has been explored for decades. Some modified gravity theories can explain certain galaxy rotation behaviour without dark matter. But the full collection of evidence is difficult to match. Galaxy clusters, gravitational lensing, the early universe, the cosmic web, and colliding clusters all place heavy demands on such theories. Still, the question is worth asking because science should not protect its favourite answer from challenge. The particle dark matter picture remains the leading explanation because it accounts for many observations at once, but the door to revised gravity has not been sealed by preference. It is tested by evidence, as it should be. The strange thing is that all of these possibilities may sound exotic, Yet the original dark matter problem already tells us that the familiar answer is not enough. Once ordinary matter is ruled out as the dominant source, we're already beyond everyday intuition. Whether the answer is a WIMP, an axion, a sterile neutrino, a hidden sector particle, a primordial black hole, or something no one has yet named, the conclusion is the same. The universe is not made only of the kinds of matter that easily become visible, touchable, chemical, and warm. The visible world is not false, but it is incomplete. The table is real, the stars are real, your breathing is real. But the gravitational structure around and between galaxies suggests another ingredient, one that does not join our ordinary sensory life. This is why the continued hiding of the dark particle is not merely frustrating, it is instructive. It tells us that our instruments must become more varied. It tells us that the first obvious search strategy may not cover the true answer. It tells us that dark matter may occupy a region of nature where known forces barely reach. If WIMPs were a first map, then the unexplored territory beyond them is now being filled with new paths. Some paths go to smaller masses, some to larger ones, some to wave-like fields, some to hidden forces, some to rare cosmic signals, some to precision experiments where the smallest shifts in ordinary systems might reveal a dark influence. The future of the search will probably not rely on one kind of experiment. It will be a network. Underground detectors will keep listening for rare interactions. New technologies will search for lighter candidates. Telescopes will continue mapping galaxies, clusters, lensing patterns, and possible signals from dark matter-rich regions. Particle colliders will search for invisible particles and new mediators. Gravitational wave observatories may offer clues about compact dark objects or early universe phenomena. Cosmological surveys will measure the large-scale structure of the universe with increasing detail, testing how dark matter clumps, flows, and shapes the cosmic web. Each method sees a different shadow. Together, perhaps, they may reveal the object. There is a good reason to be patient. The history of physics is full of hidden things that took a long time to become visible. Neptune was inferred from the motion of Uranus before it was observed. Neutrinos were proposed to explain missing energy and radioactive decay long before they were detected. Gravitational waves were predicted for a century before instruments became sensitive enough to observe them directly. The Higgs boson was part of theory for decades before a collider finally found it. In each case, the unseen was not unreal simply because it was difficult to detect. But difficulty alone does not prove existence either. The lesson is not that every hidden idea will be vindicated. The lesson is that nature sometimes requires long patience, sharper tools, and careful restraint. Dark matter may demand the same. The particle may still be hiding because our detectors are not sensitive to the right kind of interaction. It may be hiding because the signal is buried under backgrounds we have not yet fully tamed. It may be hiding because the particle is so light that it slips beneath traditional thresholds, or so heavy that it is too rare to catch easily, or so weakly connected that even huge detectors see nothing. It may be hiding because there is more than one dark component, and each contributes only part of the total. It may be hiding because our language of particles is not yet the right language. These are not excuses, they are hypotheses, and each must become testable if it is to remain scientific. The search also changes how we think about darkness itself. In everyday language, darkness means absence of light. In cosmology, dark matter is not merely darkness. It is presence without light. That difference matters. Empty space and dark matter are not the same. A room with the lights off is dark because ordinary matter is still there but light is absent. Dark matter is dark because it does not participate in light, as ordinary matter does. It can fill space gravitationally while remaining optically silent. The darkness of dark matter is therefore not emptiness, but refusal. It refuses to shine, refuses to absorb, refuses to reflect, refuses to join the familiar economy of photons and atoms, yet it accepts gravity. and gravity is enough for the universe to notice. If the dark particle is still hiding, then every galaxy is a clue we have not finished reading. The smooth halo around a spiral galaxy, the motion of stars far from the centre, the bending of distant light around clusters, the arrangement of galaxies in vast filaments, the subtle pattern in the ancient background glow, all of these are pages in the same unfinished book. We can read the gravitational chapters, but not yet the particle name written in the margin. That is where the mystery remains. We know the story has an unseen character. We do not know the face. Perhaps one day the answer will come from a detector deep underground. A pattern of nuclear recoils will appear, consistent, repeated, checked by other experiments, unmistakable after years of caution. Perhaps one day a telescope will find a signal from dwarf galaxies that matches a dark matter model with no ordinary astrophysical explanation left standing. Perhaps a collider will produce a new invisible particle and related visible companions, giving dark matter a place in particle physics. Perhaps a tabletop experiment searching for axions or light-dark matter will detect a tiny oscillation, not dramatic to the eye but revolutionary to the mind. Or perhaps the answer will arrive from an unexpected direction, from an observation no one yet knows how to make. The universe has often been most generous after humans finally admitted they were looking too narrowly. And if the answer is not the WIMP will still have mattered. It organised the search, it gave experiments a target, it taught generations of physicists how to connect the early universe with underground detectors and galaxy halos. It forced technology forward. It clarified what dark matter cannot be. It turned a vague invisible mass into a set of measurable questions. Even a suspect who turns out to be innocent can help solve a case by showing where the evidence does and does not lead. The WIMP may be the dark matter, or it may be one of the great productive wrong turns in modern physics. Both possibilities are scientifically valuable, though one would admittedly make for a more cheerful press conference. There is also something comforting about the fact that the mystery remains open. Not because ignorance is better than knowledge, but because open mysteries remind us that science is alive. The universe has not been reduced to a completed catalogue. There are still questions large enough to make galaxies feel like clues, and small enough to require detectors listening for tiny recoils. There are still particles that may exist beyond our instruments, forces we may not have named, and early universe events whose leftovers surround us without touching us. The unknown is not an empty wall. It is a frontier with measurements pressed against it. For a listener drifting towards sleep, dark matter may seem far removed from ordinary life. It does not help you find your keys. It will not make the laundry fold itself, which remains a serious flaw in the laws of physics. It does not warm your hands or light your room, but it belongs to the same universe that made ordinary life possible. If dark matter shaped the formation of galaxies, then it helped create the environments where stars formed, where heavy elements were made, where planets gathered, where chemistry found its long path toward living things. The dark particle, whatever it is, may never touch you in any meaningful bodily way, yet its gravity may be part of the reason there is a galaxy here for the sun to live in, and a sun here for Earth to orbit, and an Earth here for someone to wonder about the dark. That is the quiet lesson at the end of the WIMP story. The universe is not divided neatly into what matters and what we can see. Many important things are inferred before they are touched. Gravity itself was understood through falling objects and orbiting worlds long before anyone could speak of space-time. Atoms were argued for before they were imaged. Neutrinos were proposed before they were caught. Dark matter may be another such case, or it may force us to revise our ideas in a deeper way. Either way, the search is not only for a particle, it is a search for the hidden structure of reality. So what if the dark particle is still hiding? Then we keep asking better questions. We build quieter detectors, broader surveys, more delicate instruments, and more honest theories. We let silence count as information. We let beautiful ideas face disappointment. We let new ideas enter without allowing them to escape measurement. We remember that the visible universe, magnificent as it is, may be only the bright surface of a deeper structure, and we remain patient, because the thing we are looking for may have crossed the cosmos for billions of years without needing to be noticed. Somewhere around the Milky Way, if the particle picture is right, dark matter is moving through a vast halo older than the Earth and older than the Sun. Some of it may be passing through this room right now, through the walls, the floor, the air, and the quiet space around you. It leaves no breeze. It casts no shadow. It does not warm the skin or stir the curtains. It simply continues, almost perfectly indifferent, part of a hidden mass that helps shape the galaxy, while barely acknowledging the atoms that make us. And here we are, made of the rare bright matter that can notice, measure, imagine, and ask. That may be our small cosmic talent. We are not made of the majority of matter, perhaps, but we are made of the kind that can wonder where the majority has gone. If this quiet journey through the dark has brought you a little calm, or given the night a larger shape, I would be very grateful if you liked the video and subscribed. It helps this soft corner of science reach others who may enjoy letting the universe become a little less lonely before sleep. And as you rest now, wherever you're listening from, whether the sky outside is bright or dark, whether the room is silent or gently humming, remember that the unknown is not always frightening. Sometimes it is simply patient. Sometimes it waits in the spaces between stars, in the motions of galaxies, in the silence of underground detectors, and in the questions we carry forward. Sleep well, fellow traveller, beneath a universe still hiding some of its deepest matter, still turning, still holding its secrets quietly, and still inviting us, one careful thought at a time, to listen